Okay, let's get started. Hello, everyone. Good morning, good afternoon, good evening, depending where you are. So first of all, let me welcome you to our tutorial, tutorial, Deep Learning on Graph for Natural Language Processing. My name is Lin Fei Wu. I'm currently a principal scientist at JD.com. JD.com is the largest e-commerce platform in China. Okay, so then let me also introduce my best colleague and friends, and also the co-presenter of this tutorial, Dr. Yu Chen from Meta AI, previously was Facebook AI, and Professor Hen Ji from UIUC and Amazon, and Dr. Yunyao Li from Apple, and Professor Bang Liu from University of Montreal and Milan. So hi guys, would you like to say hi to our audience?
Hi everyone.
Hi everyone. Welcome to the tutorial.
Okay.
Okay, then let's get started. So this is the outline of the tutorial. Basically, we have three different parts. So we will, first of all, we will talk about why we care about a graph for NLP, and what's a conventional method, machine learning method for NLP. So one thing to note that the machine learning on NLP is not a new topic. It has been in the community for 2 decades. So, but with the rising of the deep learning, they definitely have a lot of new methods that have been arising in the previous several years. We call it deep learning on graph. And we will talk about the foundation and the models in this domain, and which will serve as a very important part for our second part, the DLG for NLP foundations. So later, so in the second part, you and I will talk about, so given a text sequence, how can we construct a graph that for various of the NLP tasks? And then when we have a graph at hand, how can we determine the best graph representation learning method for your NLP problem? And we also will introduce a popular line of the research direction we call the graph-based encoder-decoder model for NLP. And so in the third part, so Hen, Yunyao, and Bang will talk about how to leverage the power of the graph units for variants of the NLP tasks, such as information extraction, machine reading comprehension, natural language generation, and text mining, text clustering, matching, text mining, and classification. After that, we will also briefly introduce our DLG4NLP demo, which we try to introduce our graph for NLP library, which is the first library for promoting easy use of the graph neural nets for various NLP tasks. And then we will conclude this tutorial with the future directions. Okay, let's go to introduction. So first of all, so why care about graph? That's really because that the graph is very generic language that are able to describe and modeling a very complex system. But graph structure itself, is very simple. Just show you the right-hand side. So in a graph, you have a bunch of the graph nodes, which are able to represent different objects. And we also have an edge that connect any of the two graph nodes, which is to denote to some relationship between two graph nodes. Sometimes you can also think about translate this relationship as like a similarity between two graph nodes. Therefore, that they have some correspondence between each other. So let's take a real example. So imagine this is a teacher-student graph. Okay, so in this graph, so some node is a teacher, some node is a student. And imagine this is kind of like application from the AI plus education. And here also, each of the teacher, they may have some corresponding attributes. For example, which kind of class is the teacher teaching, right? Is what's the ranking of this teacher, kind of position of university and gender information, and same information that we'll have in the student node. So when we talk about the deep learning on graph today, we are talking about a bunch of the methods that are take input like graph topology as one part of input, and also the corresponding side information, such as the node information or edge information. So, graph structured data is really everywhere. So ranging from the social network and the information retrieval, this is very naturally, have all kind of graph data available. Even in the finance domain, so if we treat this transaction flow between the institution and each of the customer, we also can formulate this financial transaction network. Okay, and in the today, the drug discovery is a very hot topic where people try to come modeling the chemical compound as a graph, and hopefully to learn a distribution of these different drugs among the graphs, and then to generate a new graph which is represents as kind of a new drug with a certain property. Okay, for example, to combat the COVID-19. So in the program analysis domain, people are also leveraging, for example, the control flow graph or data flow graph or even other construct graph for a program analysis. Even in the well-known computer vision domain, you can still using construct a high-level graph to do the reasoning over an image. So the graph is also ubiquitous in the NLP domain as well. So that's really because the human language is a very high level simple. Okay, so that means that so you can find many hidden structure information behind a text sequence. So this is actually a long-standing problem in NLP, right? So if you care about the sentence structure, you can always use different kind of a parser tool, like a dependence path tree or constitution tree to analyze the kind of sentence structure. If you want to know the semantic information about the sentence, you can also use it, for example, the AMR parser, the abstract meaning representation, and IE graph to know the semantic relationship giving a text sequence. In some specific application, right, like a SQL language, so you can also construct a graph using a SQL query. That's really because that the different condition in the sequence clause, they don't really have all the information. Graph actually is a better representation for that. So this is really motivate us, right? Why we care about graph. And right now, let's talk about, so what's a conventional machine learning method on graph for NLP? First of all, let's take a look. So what's the current way to represent a natural language? Okay, they typically have 3 different ways. So in a very, very early stage of the NLP, people try to represent a natural language as back of the tokens. So this is very natural, just showing the right-hand side. So let's say we have 3 sentences. Okay, welcome to attend our DLG4NLP tutorial. In this tutorial, we will present how to using graph neural for NLP. And once we have this kind of different sentence or document, we tend to represent each of the sentence or document use a sparse vector, and each of the slot is a token. Okay, and I'll try to count how many numbers the token appears in the whole corpus. Okay, and then we can using this sparse vector representation, you either use like backward or TF-IDF, right, to represent each of the sentence, and then you can use that for some downstream tasks such as like text classification. Of course, you can also use a topic modeling, right, to represent the text as a mixture of the topics. And later, people found that they are also very useful to represent natural language as a sequence of a token. And this kind of a technique really is because the rising of we call the word-to vector of type of the technique. So people found that so it seems like we are able to transform the each of the word token into latent space, and then to present each of the word token as a dense vector, which is able to preserve the proximity or context information in the original text. Okay, and so here the most well-known example is like king minus man plus woman equal to queen. So this is one of the very famous example people have been using when we're using the word to vector technique. And so the third type of the way to represent a natural language is as a graph, right? As we mentioned, there are many different kind of like syntactic or semantic graph you are able to use. At the same time, right? Even in these slides, we can see that so you can easily define a text graph as a hierarchical graph, which is contain a different element like document, sentence, and a word. So because of the perspective to using graph technology, right, we are able to develop a bunch of the graph-based methods for NLP. So they even have a book that published by the Mahase and other professor in 2011 to talk about all different methods. And so here I just give a kind of example. Okay, not I'm going to list to enumerate all the methods for NLP, but just an example here. So for example, people using random walker algorithm try to obtain the stationary distribution of all the graph node, and then use that vector representation to do like a semantic similarity of text, or to do the naming disambiguation task. People are able to also use like graph clustering algorithm for doing the like text clustering task. Okay, and also, so if you have, if you want to deal with like a textual entailment task, you are able to, using graph matching algorithm to try to compute similarity between two graphs that are formulated by a text. And the people are also using like a label propagation algorithm, try to learn the label through propagation from the label data to the unlabeled data, and then to do like a sentiment analysis task. So with all this background, so nowadays we all know that deep learning showing a great power, right? In almost past like 10 years, starting from the 2012 from ImageNet, and now people have been tend to develop a different kind of method through using the deep learning technique on graphs. And now let's talk about a different kind of method. So first, this is really an image to show you that how hot topic that graph machine learning have been developed in the last few years. So we can see that the number of the submission in the archive really is exponential growing in this area, especially from the 2016. This is really the first modern deep learning technique on graph have been developed in this year, and let us see that is the number of submission is growing a lot. So this is kind of like a brief history to introduce graph neural nets. So we can see that in the 2009, this is really the first paper that people developed using graph neural nets. But this paper is very interesting, right? Because it's published in 2009. It's even before we have been widely recognized as the deep learning in 2012. But after 4 years, right? So people have been trying to using the modern deep learning architecture on this topic. So in 2016, the first GIO-based modern graph neural nets, gated graph neural nets, is developed, published by Dr. Yujia Li from the DeepMind. And so later, the people also published the first graph convolution-based method called graph convolutional network. This is really a paper that started a new era of the graph neural history. And people have been seeing that, so we have been using this. This is really showing that so the graph neural is so powerful, so that we are able to use that for solving many problems. And then starting between 2017 and 2021, we have been seeing that a series of the graph neural method, like based on the graph convolution, message parsing, attention-based method, unsupervised graph neurons have been developed, and it's really have been is really in the fast track that boost a lot of the good algorithm. At the same time, we can see that from the 2019 and 2021, there are a bunch of the people, especially from industry, they have been starting to leverage a power of graph neurons for various applications, such as a search, recommendation, drug discovery, NLP, intelligent transportation, and so on and so forth. And also we have seen a bunch of the very good high quality open source library have been released. For example, for the general library, like deep graph learning and PyTorch geometric, is really two very, very top library people have been leveraged for using graph neurons. At the same time, we also see that a lot of dedicated library have been developed. For example, the graph NLP library that we developed over last year, and for the various NLP problem. And the Torch Drug is a library that try to leverage the power of the graph neurons for the drug discovery. Okay, and we also seen that starting from the 2021, there are a bunch of the graph neural books that have been released. For example, the 3 books that almost released at the same time on the same year. So one from the Tsinghua University, they published the first book called The Introduction to Graph Neurons. This is very a small book, but it's a very early book on this. try to summarize all different kind of graph neural methods. And later, so now Professor Jian Tang from MSU, they published a book called The Deep Learning on Graph. So this is to try to summarize all the research going on in his lab, and to give a very good comprehensive way to introduce deep learning on graph techniques. And Professor Hamilton also give a book called The Graph Representation Learning. This is a very short book, but it's a very good book to summarize his PhD. This is like many well-known methods developed by his advisor, Yuri, from Stanford University. And so luckily, early this year, 2022, we also published the first most comprehensive graph neural book. It has 27 chapters with almost 725 pages. And here we try to publish a book that to summarize as much as possible about the foundations, the frontiers, and applications people have been using so far for this very fast and growing area. Okay. So now let's talk about a little bit about the graph neural foundations. So the process of the node embedding essentially is try to learning embedding of each node in a graph through by processing the initial adjacent matrix and also the initial node embedding. So depends on the type of the graph filtering operation, which is really differentiate different type of the graph neural method. For example, we can generally cover them into the four different groups: the spatial-based method, spatial-based method, attention-based method, and the recurrent-based method. However, the graph filtering operation don't really change the graph structure. Therefore, so if we want to learn the graph level embedding, so we have to introduce a new operation called the graph pooling operation. The graph pooling operation essentially will take the initial graph structure and the node embedding and to generate a smaller graph with a fewer node and with corresponding new node embedding. We can generally group them into two different groups. The first one is a very common one. We call the flat graph pooling. So here you can use like max pooling, average pooling, mean pooling. This is a very simple operation, but it works very well in most of the NLP tasks. Of course, people are also to try to develop a more advanced technique, try to do the graph pooling. For example, the hierarchical graph pooling, essentially try to leverage the coupling technique, try to reduce the graph size each layers and finally to stack the representation of the graph level representation for each layer as a final representation. So now let's give a very kind of like simple example to go through a very basic model for graph neural, so that I don't know how much background you have in this domain. Hopefully after that you will have a very quick idea about what is graph neural about. So if you don't know about the GN before. So the key idea here is that essentially try to generate a node embedding based on the local neighborhood. Just as show you this figure, right? You have an input graph, you have a target node. So if we want to learn the embedding of the target node A, we can leverage its neighborhood information like BCD. This is the first order neighborhood, and use that context information to generate the representation or embedding for the node A. And therefore that you can define a unique computational graph for each of the graph node. Okay, and then you can define a neighborhood application function. And in the first layer, you have an initial node attribute, and then you can have as much as the layers you want to do the message propagation. However, in practice, it's not possible to have a very deep. Okay, we'll talk about that later, because this is essentially a very active area called over-smoothing problem. That you often have overfitting if you have a very deep layers. Okay, and so, but essentially, conceptually you can have as many layers as you want. Okay, so in the second layer, so then in the first layer, then you will aggregate all the information that you have in the first layer, and then to generate a representation for your target node. And then you propagate this information through the network, and then to learn the second layer, and so on and so forth. So that then every node will generate an embedding for the corresponding node. Okay, and so here let's take an overview of the graph neural model. So first thing you want to do, you want to define a neighborhood aggregation function where you can, for example, you can aggregate the representation from A and C, and then to generate the representation for B, and same thing for C and D, and then propagate to A. And then you just need to, once all the graph node have learned the corresponding embedding, then you can define a loss function on the embedding, for example, to doing like a node classification task, and then you can learn a model and train it on the set of the node, and each of the node is a batch of the computational graph, right? And then you can generate a node embedding for each of the node as you want. The good thing about this is that since you are defining an aggregation function to learn a parameter for aggregation function, therefore you are also able to even generate a node embedding for the node that you never see in the training phase. Since that you are learning any parameter for corresponding node, if you have a new node coming in the testing phase, you are able to use an aggregation parameter, right, to generate the embedding for that. So now let's take a very case study, right, to talk about this. So we can define like this aggregation function as an average function. This is probably the most simple way that you can define, right? Then you can just average the message from the neighborhood, and then just apply the graph units and the units to learn the parameter, and then to do the application function. This is the basic math behind what we discussed in the previous several slides. So as a beginning, right, you have an initial layer 0 embedding. That's essentially kind of like an initial node attribute. Okay, and then transform that to the latent space, and then you can do in the red box, it's showing that it's average for the neighborhood the previous layer embeddings. We call them message. Okay, and once you have that, then you can using you can fill in the information from between the message and also the embedding from the previous layer for the target node, and then to do the activation function to generate the embedding for the current layers. So this is like a quick summary to summarize what we discussed here. So the key idea here is to generate the node embedding by aggregating the neighborhood information. And here we can allow for the parameter sharing in the encoder, and also allowing for the inductive learning. So today you will see a lot of the different graph neural method, and this is probably summarize the most popular model here. But all the models actually differ only in the graph filtering operation. Okay, so for example, the spectrum-based graph filtering, the most famous method probably is the GCNs. This is probably the most cited paper in this domain. So where they try to define a graph filter operation using a graph Laplacian Fourier domain to transform everything in the Fourier domain. We'll discuss this in details. And the spectrum-based method try to aggregate the messages through the spatial neighborhood instead to tackle this problem from the transformed Fourier domain. And the attention-based method is a kind of method actually very close to the spatial method, but you try to calculate the importance of each neighborhood so that you are able to learn. You are not simply treat each neighborhood equally because they are different. So you want to use attention to capture that. And finally, the use recurrent-based method is try to tackle the directed graph at the same time try to generate the representation not only for a single graph, but it can be deal with to generate a sequence of graph. So the first one is called the key idea is for graph convolutional network. So the key idea here is that we try to apply a spectrum convolution on graph. So where we define a multiplication between a signal xi and the graph operation in a Fourier domain, parameterized by the theta parameter. Okay, and the U here is essentially is an eigenvector for a normalized graph Laplacian. But you can see that if we want to do that way, you have to do the eigen decomposition. The eigen decomposition is so expensive. So especially when your graph is really large, right? So therefore, the people think about how to accelerate this computation by leveraging a chip-shape polynomial. However, it's a very good approximation, but still it's not powerful enough. So and then later in the GCN paper, they try to develop this called the first order approximation by cut off the Taylor expansion and only preserve the first order approximation. Okay, and this has become very fast because right now you only have the matrix vector operation, right? And it's fast and see that although it's approximation, but it's so powerful. And you just need to do this renormalization trick in order to stabilize the numerical computation. And this GCN method have been widely used for the many NLP tasks, such as in the text clarification, question answering, text matching, topic modeling, and so on and so forth. So the second type of method that we call the message passing neural network. That is the key idea here that so instead of doing the spectrum convolution, right now you cast this graph convolution as a message passing process. Okay, so there are two typical methods here. The first one called MPNN. So MPNN is a very generic learning framework to do message passing. So basically, they define two generic functions called the update function and aggregate function. So where they can, in the aggregate function, you take the input of the node and the edge embedding, and then try to aggregate the information to formulate the message. And the message will propagate through the network and then to fuse with the previous embedding for target node. And then we can define this update function, and then to generate a new embedding in the current iteration. However, it's also very expensive. Think about that if you try to aggregate all your neighborhood, right? If the number of the neighborhood is very large, that's make it computationally very expensive. So therefore, so people try to improve this method by proposing a graph stage. So graph stage is kind of like a simple version of the MPNN in the sense that so it's only considered node embedding, and more importantly, they are not to try to aggregate all the neighborhood node. They only try to sampling the certain ratio number of the neighborhood, so that you can do two good things. First thing that so you are able to accelerate computation. Second thing that you are able to overcome the oversmoothing problem. So or overfitting problem. Sorry. So that therefore that so this is really good acceleration, and also try to overcome this certain previous problem. And so MPNN and the graph stage method have been also widely used for many NLP tasks, in the node graph, information extraction, and the semantic parser. So the graph attention network we call it a GAT. The key idea is very simple. It's just try to dynamically learn the weights on the edge. Why they care about that? Because the previous method all assume that all the graph node or neighborhood contribute equally to the target node. But reality maybe not, right? Maybe some node is more important compared to other node. Therefore, that to dynamically learn this weight and then to perform a weighted average of all the node embedding, it definitely makes sense. So in order to achieve that, so they actually borrow some idea from the transformer to using the self-attention to learn a local weight, and then they compute that to generate the final node embedding. GAD probably the second most used graph neural method in all the NLP tasks. So the final one is called gated graph neural nets. So this one is key idea, try to using the gated recurrent net unit while taking into the account edge type and direction. So we can see here that so there are two things to consider. One, they're doing a lot of padding, right? And also you can see that they actually treated the edge, split them into the incoming and outgoing. Therefore, that they can directly deal with the directed graph. At the same time, they will form this augmented matrix to do the computation. And finally, that they're using GRU unit instead of using a simple NLP to fuse the previous node embedding and also the message. Therefore, so this is actually the first modern paper for graph neural nets. Okay, so now I finish this basic introduction about our DLG4NLP. So in the following part, we will talk about the key foundations of the DLG4NLP, where we'll talk about the graph construction method, and we'll talk about the graph reinforcement learning method, and also we'll talk about the graph-based encoder-decoder framework. And finally, we'll go through a lot of the different applications, try to illustrate how to leverage the power of the graph nets to tackling various NLP problems. And later we will talk about our key library called the graph NLP library, and this is the first library that have been developed for this domain. And finally, we will conclude this tutorial with a future direction. And with that, I will give my floor to my colleague Yu, and to continue this topic.
Yeah, thanks, Linfei. Let me first share my screen.
Do you have time for questions?
Oh, yes. Yeah. So you can ask question now, or you can present question later. So we will have a Q&A session to concentrate on various problems.
We just try to understand, better for some basic concept to understand later. So is this embedding, you use the example of the node, but is embedding on the node, or it has the graph of certain length?
So the embedding we talk about here is a node embedding. So giving a graph, right? So giving a text, you formulate that as a graph, and later then we have to learn the embedding for each of the graph node. And some of the graph node will be represented by the word token that previously given from the input. So maybe you can preserve this question later, because when we illustrate in how to construct a graph, you probably will know better about what a graph node we're talking about, and what kind of node embedding, why we learn for that.
Okay, thank you.
Okay, sure.
Great. So can everyone see my screen?
Yes, we are.
Okay. Yeah. So yeah. Hi everyone. My name is Xu. I'm a research scientist at AAAI. So next, I will talk about DLG4NLP foundations. So first, let's talk about graph construction for NLP. So as Linfei just introduced, so there are like 3 typical ways of representing text, which are bag, sequence, and graph. So among all these 3 approaches, like graph has the strongest representation power because it can capture rich and diverse information about the text. So we know that different NLP tasks require different aspects of the text, such as syntax, semantics, information. So in the meanwhile, different graphs capture different aspects of the text. So therefore, how to convert the text to a graph is an important yet challenging problem, which really depends on which aspects of the information we want to capture in a text graph. So in general, we group various graph construction approaches into 2 categories. One is static graph construction, and the other we call it dynamic graph construction. So we will introduce each of them and summarize their properties next. So note that the primary goal of graph construction we are talking about in this tutorial is to achieve a good downstream task performance. So we will not care very much about, for example, the interpretability of the constructed graph, especially for dynamic graph construction approaches. So first, let's talk about static graph construction. So it aims to convert the raw text to a graph where text can be either a sentence, a paragraph, a document, a corpus, and so on. So this is usually conducted during the pre-processing stage by augmenting the raw text with various domain knowledge, such as syntax, semantics, topic, co-occurrence, and word knowledge. So many static graph construction approaches used in practice are driven by the particular NLP applications and incorporate hybrid prior knowledge about the data and the task. So let's see some representative static graph construction approaches for NLP, which are widely used in the existing literature. So the first static graph construction approach we are going to talk about here is dependency graph. So as we know that dependency parsing aims to assign a tree structure to a sentence, which describe a set of directed grammatic relations holding among the words. So it can help extract the subject, verb, object triples that can be that are often indicative of the semantic relations between predicates. So it could be very helpful for many NLP applications, such as information extraction, semantic parsing, core reference resolution, and question answering. So for dependency graph construction approach, specifically given a sentence are there other jobs outside Austin? So we can apply dependency parsing tools to convert it to a graph. So this. So but what if we have like multiple sentences in text? Because usually we apply dependency parsing to us at a sentence level. So one common way to do that is to add additional sequential edges between the nodes so that we can connect multiple dependency graphs in a paragraph. Besides, this can also help reserve sequential information in raw text, which can be helpful in some NLP applications. So the next static graph construction approach we will introduce is constituency graph construction. So the constituency graph is able to capture phrase-based syntactic relations in a sentence. So for instance, given a sentence, we can apply constituency parsing tools to convert it to a graph. So for the same reason, we can add additional like sequential edges between the nodes. So next, let's talk about AMR graph construction. So AMR graph captures various semantic information of the sentences, such as like semantic rows within sentence, core reference, named entities, and so on. So they preserve the semantic meanings of text while abstracting away the syntactic representations. And that can help like complement the raw text by providing high-level abstract information. So given a sentence, like Paul's description of himself, a fighter, we can apply AMR parsing tools to convert it to a graph. So the IE graph aims to extract the structural information from text to represent the high-level information about the entities and their relations. So given an input sentence, given an input text, we can apply IE tools to convert it to a graph, which contains entities such as Seattle as nodes and the relations such as attended as edges. So co-reference resolution is usually conducted here to group entities which refer to the same concept to a single node. Like here, we have Paul, he, a renowned computer scientist. So these three entity mentions, they actually refer to the same concept. So we can group those entity mention nodes to a single node. Next, let's talk about the knowledge graph construction approach. So the knowledge graph stores word knowledge about entities and their relations. So given a question like who acted in the movies directed by the director of Some Mother's Son. So we can first identify the top entity of this question, which is Some Mother's Son, and then extract a subgraph from a knowledge graph, which surrounds the top entity and hopefully contains answer entities of this question. So let's talk about the topic graph construction. So topic is basically a subject that text is about. So different documents might mention overlapping topics. So we can discover the relations among documents by comparing their mentioned topics. So another way to find connections among texts is to compute their pairwise similarity scores. So, and one common way to compute the similarity scores is to first embed the text to some like vector representations, such as TF-IDF vectors, and then we can compute the pairwise similarity among different, for example, documents in that embedding space. So in order to capture the word co-occurrence information, we can regard the co-occurrence matrix as an adjacency matrix. And then we can construct a graph containing each unique word as a node. So this is how we can construct a co-occurrence graph. So next, let's talk about like SQL graph construction. So some logical forms such as a SQL query can also be naturally represented as a graph, which can well capture the relations among various objects. So far we have discussed the many common static graph construction approaches, which preserve some kind of prior or domain knowledge. So in practice, it might be beneficial to construct some hybrid graph capturing multiple sources of prior or domain knowledge, which is usually tightly coupled to the NLP task at hand. So far, as we already see, like static graph constructions operated by augmenting text with various domain knowledge during the pre-processing stage. So those domain knowledge could include like syntax, semantics, topics, co-occurrence, and so on. So for each type of domain knowledge, there are like various types of graphs we can construct. So which static graph to construct really depends on the specific NLP applications. So for instance, for the task of multi-hop machine reading comprehension, so information such as like entities, entity co-references across the documents are usually quite helpful. So this kind of static graph constructions can be helpful for this task. So as we will see in the application part of this tutorial, like these static graph construction approaches are widely used in various NLP applications such as information extraction tasks, natural language generation tasks, reading comprehension tasks, and text classification tasks. So yeah, that's for static graph construction. Next, we will talk about dynamic graph construction, which shares the same goal with the static graph construction. But unlike the static graph construction, which is performed during pre-processing, dynamic graph construction operates by jointly learning the graph structure and the graph representations on the fly. So the ultimate goal is to learn to optimize the graph structures and the graph representations with respect to certain downstream NLP application task. So we summarize the typical dynamic graph construction pipelines as the following. So given a set of data points, where each data point can like stand for various NLP elements such as words, sentences, documents. So we first apply graph similarity metric learning, which aims to capture the pairwise node similarity, and the returns are fully connected weighted graph. Then we can optionally apply some graph specification techniques to obtain a sparse graph, which I will talk about in more details later. So if the input data is instead of data points, but also an intrinsic graph containing edges, so we can also optionally combine the intrinsic graph and the learned implicit graph to form an augmented graph. So the output graph will be consumed by a subsequent GN-based module to predict to learn graph representations and produce task-dependent outputs. So next, we will introduce each of the 4 dynamic graph construction techniques, which we summarize from the existing practice of its applications in the NLP field. So these techniques include the graph similarity metric learning techniques, graph specification techniques, like how to combine intrinsic graph structure and implicit graph structures for better performance, and also various graph structure learning paradigms. So let's first talk about graph similarity metric learning. So the idea of graph similarity metric learning is to compute the pairwise node similarity in the node embedding space and obtain an adjacency matrix based on that. So it can enable inductive learning because once the similarity metric learning is finished, one can apply it to unseen nodes to learn a graph. So this is very important for many NLP applications because we want to learn a new graph for each new text example during the inference phase. So variance metric functions have been proposed by previous works for graph similarity metric learning. So we group those metrics into 2 categories. One is node embedding based similarity metric learning, and the other is we call it structure aware similarity metric learning. So we will talk each of them in next few slides. So let's first talk about node embedding based similarity metric learning. So we are given a set of data points and their vector representations, and we can apply variance metric functions to learn the pairwise node similarity. And the output is the weighted adjacency matrix, which is corresponding to a fully connected weighted graph. So common metric functions for this purpose include like attention-based and cosine-based functions. So let's first talk about like attention-based graph similarity metric functions. So let's see 2 typical variants. So in variant 1, VI is the node embedding, and the U is the non-negative vector, weighted vector learning to highlight the different dimensions of the node embedding. So they have the same dimensionality. In variant 2, so here W is a learnable weight matrix, which learns to map the node embedding to a latent space, where we can compute the node pairwise node similarity. And here the ReLU activation function is used to enforce the sparsity of the similarity matrix, which can be helpful. So in both of these two variants, dot product is used to compute the pairwise similarity. Let's see an example of cosine-based metric function. So here, WP is a weighted vector associated to the piece perspective, and it has the same dimension as the node embeddings. So intuitively, Sij P here computes the pairwise cosine similarity for the piece perspective, where each perspective considers like one part of the semantics captured in the embeddings. Then we can average like multi-header similarity scores here to increase the learning power of the metric. So this kind of strategy is kind of similar to the idea of multi-head attention in transformer models, and it usually works pretty well in practice. So now let's talk about another type of graph similarity metric learning function, which is called structure-aware similarity metric learning. So unlike the previously like node embedding-based metric learning, so this metric learning approach, in addition, considers the existing edge information of the intrinsic graph when it's available, because in some NLP applications, we do have some reliable intrinsic text graph we can utilize, and we don't want to like totally discard like those useful information. So let's see two examples metric functions belong into this category. So in these two variants, attention-based function is applied, and notably, the edge embedding of the intrinsic graph, EIJ here, play an important role in learning the implicit graph structure. Okay, right. So now let's move to the graph specification techniques. So far, we have seen some similarity metric learning functions which can learn a fully connected graph. However, a fully connected graph is computationally expensive and might introduce noise. And we might want to enforce sparsity to the learner graph structure to obtain a sparse graph by leveraging like variance techniques, which we will introduce next. So for KN style specification techniques, so for each node, only the K nearest neighbors and the associated the similarity scores will be kept, and the remaining similarity scores will be marked off. So as a result, we can get a sparse graph from the fully connected one. So for epsilon neighborhood specification techniques, those elements in the attention matrix which are smaller than a non-negative threshold epsilon will be masked off. So we can also get a sparse graph by doing that. So besides explicitly enforcing the sparsity of the learner graph by applying certain form of threshold, either it's like a K for KN or epsilon for epsilon neighborhood specification, sparsity can also be enforced implicitly, but in a learning-based manner. So for example, we can apply certain form of graph regularization to the learner adjacency matrix to enforce sparsity. So now let's talk about how we can combine intrinsic and implicit graph structures and why we want to do that in some scenario. So we know that the intrinsic graph typically still carries like rich and useful information regarding the optimal graph structure for the downstream task. Some recent works propose to combine the learned implicit graph structure with the intrinsic graph structure based on the assumption that the learned implicit graph could be regarded as a potentially shift from the intrinsic graph structure, which is supplementary to the intrinsic graph structure. So one common way to do this kind of combination is to compute a linear combination of the normalized graph Laplacian of the intrinsic graph structure and the normalized adjacency matrix of the implicitly learned graph structure. And we can apply like variance normalization of operations here to the learned adjacency matrix, such as like a graph Laplacian or like a low normalization. Okay, let's talk about the variance techniques, variance like learning paradigms for dynamic graph conjunction. So like which has been explored in the existing literature. So most existing dynamic graph conjunction approaches for GNNs consist of two key learning components. One is graph structure learning component, and the other is graph representation learning component. And the most straightforward strategy is to jointly optimize the whole learning system in an end-to-end manner towards the downstream like prediction task. So in order to capture long-range dependency in a graph, we often like stack multiple GN layers so that the graph representations are consumed and transformed by each of the GN layer in a sequential manner. So this is quite common in GN practice. So in terms of like a dynamic graph conjunction, another common strategy is to adaptively learn the input graph structure to each stacked GN layer to reflect the changes of the intermediate graph representations. So this is actually like similar in spirit to how transformer models learn a different attention matrix in different layers. So if we regard an attention matrix learned by a transformer model as an adjacency matrix of a fully connected graph. So let's talk about another learning paradigm for dynamic graph conjunction, which we call it iterative learning paradigm. So unlike the above two paradigms, recent work proposed to propose an iterative graph learning framework by learning a better graph structure based on better graph representations, and in the meantime, learning better graph representations based on a better learned graph structure in an iterative manner. So as a result, this iterative learning paradigm like repeatedly refines the graph structure and the graph representations toward the optimal downstream task performance. And variance stopping criterion can be applied for this iterative learning process. For example, we can stop the iterative process when the difference between the learned adjacency matrix and the consecutive iterations is small enough. Okay, so far we have introduced various dynamic graph conjunction techniques, including graph similarity metric learning, graph specification, like how to combine intrinsic and explicit graph structure, and various learning paradigms. So one might ask, like, how is a static graph conjunction compared with the dynamic graph conjunction? Like, which one should we use given a task? So let's first talk about the static graph conjunction. I think the biggest advantage of static graph conjunction is it can easily encode the rich prior knowledge in graph, which can be very helpful for certain NLP applications. But this can also become a downside when it's expensive or not very durable to obtain such extensive domain expertise. For example, for some low resource languages, we might not have a rich prior knowledge to utilize. Besides, static graph conjunction can also be error prone due to the noisy or incomplete graph, and therefore is often suboptimal. And due to its disjoint graph construction and graph representation learning nature, it can also lead to error accumulation. So compared to static graph conjunction, dynamic graph conjunction is quite a new area, and it has not been extensively studied in the DLG4NLP area. Its advantages include require no domain expertise, and the joint learning of graph structure and graph representations. So currently, dynamic graph construction also has some variants like disadvantages, such as the scalability issue, because we needed to compare the pairwise node similarity, which requires at least like O of n squared. And also the explainability issue. If in some applications, explainability of the constructed of the graph construction is an important factor. So, but these like growth areas are also some good future directions. For example, there are very active research working on how to improve the scalability of dynamic graph construction approaches by leveraging some techniques like kernel-based methods, like random feature-based methods, nested methods, and so on. Yeah, so now it comes to the question, when to use which. So based on our study and the practice, so we think it's best to use static graph construction when we have domain knowledge at hand which fits the task and can be represented as a graph. And for dynamic graph construction, so here might be some reasons why we want to look into that, including one, lack of domain knowledge which fits the task or can be represented as a graph, or two, the domain knowledge is incomplete or might contain noise, or three, we want to learn implicit graph which augments the static graph. So basically, we want to combine the benefits of both the static graph construction approaches and the dynamic graph construction approaches. Yeah, so that's for the graph construction for NLP part. Next, I will talk about the graph representation learning for NLP part. So let's briefly recap on the DLG4NLP pipeline. So given a graph, so we usually will need to like first construct a graph, and then we apply some graph representation learning methods, which are usually like a variance graph neural networks. Then we can have like a prediction module to produce the tasks dependent outputs. So given a graph, we will need to decide like which GCNs to apply for graph representation learning. So this is a very critical problem. We needed to think about when we apply GCNs in real world applications. So in this part of the tutorial, we will try to help answer this question. So let's first review some definitions on like the various types of graphs. So these concepts are important since we will mainly depend on the graph types to choose which GCNs to apply. So in general, we can categorize graphs into three types, which are homogeneous graphs, multi-relational graphs, and heterogeneous graphs. Which depends on like the number of node types and the number of edge types. So if the number of node type is 1 and the number of edge types is also 1, we call it a homogeneous graph. If the number of edge types is larger than 1, we call it like a multi-relational graphs. Otherwise, we call it heterogeneous graphs, which usually have more than one type of nodes. So let's see the like overall load map on which GCNs to use given a graph. So this actually like works like a decision tree, which we summarize to help you make this decision, which GCN to use for a given graph. So in short, we will decide whether to apply homogeneous GCNs, multi-relational GCNs, or heterogeneous GCNs based on the input graph types. So let's first talk about homogeneous GCNs for NLP. So when to use homogeneous GCNs given a graph, if it's a homogeneous graph, then we can of course we can like apply homogeneous GCNs to it. Or like if it's a non-homogeneous graph, but we can choose to convert it to a homogeneous graph by leveraging some techniques which we will introduce later. Then we get a homogeneous graph, and we can also apply a homogeneous GNs to learn the node graph representations. So in terms of homogeneous GNs, basically many GNs which we are familiar with, which were introduced by Lin Fei previously, belong to homogeneous GNs, like including GCN, GAT, graph, SAGE, GGN. Yes. So as I just mentioned, like we can choose to convert a non-homogeneous graph to a homogeneous graph by leveraging some techniques. One such technique is called Lavie graph conversion. So given a non-homogeneous graph, which contains variance edge types, we can leverage Lavie graph conjunction to convert it to a homogeneous graph so that we can apply homogeneous GNs to it. So, so the key idea of Lavie graph conversion is to regard each node, regard each edge in the original graph as new nodes, and connect the original nodes and the new nodes. So as a result, we will get a bipartite graph, which is a homogeneous graph. So we can apply homogeneous GNs to it. So next, let's talk about like how to handle edge direction information, because even we get a homogeneous graph, it's possible that the edge direction information is very helpful, and we want to encode the edge direction information using our GNN. So this is actually true for many NLP applications. Just think about the success of like BI-LSTM or the BERT model. So those models all like will utilize the direction of the text. So given a directed graph, we might not be able to directly apply some homogeneous GNNs, which lead to edge direction information loss. So common strategies for handling directed graphs include one, like a message passing only along directed edges, but that's not ideal because we will lose the useful edge direction information. And two, we can choose to regard the edge directions as edge types, and then those edge types can capture the edge direction information. And three, we can design some special like GNN variants for directed graphs specifically, which can encode the edge direction information very naturally. So we will talk about the later two strategies in the next few slides. Yeah. So let's talk about the second strategy, which is to regard edge directions as edge types. So this is quite straightforward. So this usually this will result in a multi-relational graph, which has like three types of edges. One is the default edge corresponding to the original edges in the input graph, and we will have an inverse edge type, which is the inverse of the original edge, and we will also have a self edge type, which are basically we can add self loops on all the nodes in the original graph. So by doing that, the edge types can naturally capture the edge direction information, and we can apply multi-relational GNNs to the resulting graph to encode the edge direction information. And next, we will talk about the bidirectional GNNs, which are specifically designed for directed graphs. So we summarize the two variants of bidirectional GNNs. So the first one is, we call it BiSEP GNN. So BiSEP works very similar to the famous BI-LSTM model. So in the first step, we run multi-hop backward or forward GNN on the graph. We can stack many such layers, GNN layers, and at the last step, we can at the last hop of the GNN, so we can concatenate the final backward node embeddings and the final forward node embeddings to get our final node embeddings, which captures the edges from two directions. And then the second variant we will introduce here is called bifuse GNNs. So in the first step, we will run one hop backward and forward node aggregation, so which will give us two node aggregation vectors. One is for incoming edges, the other is for outgoing edges. And then we will fuse these two aggregation vectors at each hop and together fuse the node aggregation vector. Then at the last step, we will update the node embeddings using the fused aggregation vector. So we can repeat these three steps at each hop of the GNN. So then let's talk about multi-relational GNNs for NLP. So when to use multi-relational GNNs? So given a graph, if it's a non-homogeneous graph which contains like multiple edge types, we can apply multi-relational GNNs to it. Or we get a homogeneous graph, but it's a directed graph, as we previously mentioned. We can regard the edge types as the edge direction as edge types, which will give us the multi-relational graph. Then we can also apply multi-relational GNNs to it. So in terms of multi-relational GNNs, we summarize different variants into three categories. One is to include the relation-specific transformation parameters in GNN. So we call it relational GNN. And the second one is to introduce edge embeddings directly to GNN message passing mechanism. And the third one, we call it the multi-relational graph transformers, which combines the benefits of both GNNs and the transformer models. So we will talk about each of them in the next few slides. Yeah, let's first talk about RGN. So RGN, which is short for relational GNN, is the most common variant, which compared to the conventional GNN, so it has two features. One, it introduces relation-specific transformations. For example, in this equation, we have data RK here. So that means for each relation type, we will introduce transformation functions to transfer the node embeddings, so that the whole process is relation type aware. And two, it will do node aggregation per relation specific subgraph. And if we apply the RGN idea to GCN, we will get the relational GCN model. So it basically introduces relation-specific node feature transformations during the node neighborhood aggregation, as we can see from this equation. So here we have a relation-specific D by D learnable weighted matrix applied to the node embeddings during the aggregation process, and we do node aggregation per relation type subgraph. Yeah, RGN is actually quite good at doing relation-specific message parsing, and hence can handle multi-relational graphs. However, it is kind of expensive because we have to learn like D by D transformation weighted matrix for each relation. And for some scenarios, for example, a knowledge graph, which has a bunch of relation types, this is quite expensive, and it's easy to overfit the data because we have too many model parameters. So there are two common ways to avoid this kind of over parameterization of RGN. So one is to introduce basis decomposition, which regards the relation matrix as a linear combination of some shared bases. So this can be seen as a form of weight sharing between different relations, and that can largely reduce the number of parameters we have. And the second strategy is it's called block diagonal decomposition, which can be seen as matrix sparsity constraint. This can also largely reduce the number of learnable parameters for RGN models. So the second type of multi-relational GNN will explicitly include edge embeddings in the message passing process. So in these two variants, so here EIJ is the edge embedding. They participate into the node aggregation process as we are seeing here. And compared to the variant 1, variant 2, in addition, updates the edge embeddings besides the node embedding. So that's the unique feature of this variant 2 strategy. And the last type of multi-relational GN we will introduce here is called multi-relational graph transformers. So transformers can be regarded as a special class of GNNs, where multi-head self-attention is essentially learning dynamic graph structures adaptively as each layer. And it actually and transformer models actually share like many similarities with the GAT models. However, the transformer models fail to effectively handle the arbitrary graph structured data, even though it introduces the position embeddings to somehow capture this kind of structural information of the input data. For example, the position embeddings are used to encode the text sequence, and people have tried to design some special position embeddings in order to capture the structure of the graph if the input when they try to apply vanilla transformers to graph structured data. But still, transformer models are not quite good at modeling the graph structure of the input data. So multi-relational graph transformers tries to combine the benefits of both transformer models and the GNN models. So basically, it made two major modifications to transformer models to make it directly applicable to graph structure data. One is to employ structure-aware self-attention, and then the second is to make the model respect variance relation types. So one such variant of multi-relational graph transformers is called RGAT-based graph transformers. So as we can see from the equations here, so here we introduce GAT-like mask attention to the attention mechanism of vanilla transformer models. So this GAT-like mask attention respects the graph structure of the input data. And also we here introduce the relation-specific learnable weighted matrix, which respects the edge type information. Next, let's talk about another type of multi-relational graph transformer models. We call it structure-aware self-attention based graph transformers. So as we can see here, so here we directly modify the attention mechanism of vanilla transformer models by introducing edge embeddings. So as a result, the attention mechanism respects the intrinsic respects the input graph structure because we have edge embeddings here. Okay, last I will talk about heterogeneous GNNs. So when to use heterogeneous GNNs, so given a graph, if it's a non-homogeneous graph which has more than one type of nodes, by the definition, we know it's a heterogeneous graph, and we will need to apply heterogeneous GNNs to encode it. We will introduce one popular variant of heterogeneous GNNs, which is based on meta path idea. So here's an example of a meta path. So given an author also know the type of pair, we can extract at least two meta paths between them. One is author paper, topic paper, author, based on the fact that an author can write a paper mentioning a topic, and the topic can be mentioned by another paper written by another author. Similarly, we can extract some other meta paths between author and another pair. For example, author, paper, venue, paper, author. So specifically, we will introduce one variant of such of meta path based heterogeneous GN called HAN. So here are three key steps of the HGN model. One is to introduce a node type specific node feature transformation. So as we can see here, WT is a node type specific learnable weight matrix. So for each type of node, we will have a corresponding weight. We'll have a corresponding learnable weight matrix. And the second step, we will do node level aggregation along each meta path. So here we aggregate over neighboring nodes in a case meta path. And in the second step, we'll do meta path level aggregation. So here we apply attention weights over all the meta paths. Yeah, so that's for the heterogeneous GNN, and that concludes the graph representation learning for GNNs. So next, I will pass it to Linfei to introduce graph encoder decoder models for NLP.
Okay, thank you. Let me share my screen. Okay, so in this part, we'll continue to talk about a popular line of research direction called graph-based encoder-decoder model for NLP. So before I start that, I would like to start from the sequence model that people typically have been using. So for those who are not really familiar with sequence model, you can think about that. So this is essentially a model originally developed for machine translation. You have a sequence input, you have a sequence output. You won't have a neural network model to learn a mapping between sequence input and output, so that you can learn the either translation or some kind of a mapping between them, so that you can do the downstream task. So what kind of application we typically use? So it's starting from the machine translation, but people later found that it's very useful for any kind of generation task. So therefore, the later people have been using that, for example, for natural language generation, logic form translation, information instruction. So the challenging here really is, so when we try to apply sequence model, it's only suitable for a task that your input is represented as a sequence. But just as we mentioned here, right? So the sequence input essentially can easily transform as a graph input, which may contain much more information. Therefore, that the sequence model can really deal with this complex structure. And second thing is, so if we already have a graph input, so if we want to use the sequence model, you have to convert the graph input into the sequence. That will definitely lose information. So, and other possible situation that, so you may want to, like just as we mentioned, right? There's so many ways to augment the original sequence with many additional structure information, and that will definitely enhance the sequence feature. So here we introduce the first model called the graph to sequence model. So this is a very generic model when we proposed in 2018. Now it looks like a very simple model. Essentially, you can think about that it's have two parts. One is a graph encoder, other one is a sequence decoder. And of course, we want to have attention to enhance the model. If you're familiar with sequence model, you will know that how importantly the attention mechanism is for a sequence model. So essentially, in this model, we are basically try to split the incoming argument age, and therefore so we can develop what we call the bi-directional node embedding that we previously have been introduced a little bit. And so then once you learn the node representation for each graph node, you can doing MLP to formulate, for example, use a mask pooling to formulate a graph level embedding that will pass to this sequence decoder. So sequence decoder will take that as a initial context, and sequence decoder later will also each of the when you do the decoding, you will also attend this context vector to the input part, that is a graph structure, right? And then try to find out so what's the most relevant graph node to the current decoding state. And then you will highlight the most relevant one, and then to generate a good current token out of this sequence decoding state. and then you will continue this finally to generate a whole text sequence so that you can finish the task. So more specifically, the bidirectional graph neural for direct graph, we can have two different versions. One is a bisect. So we have already introduced this. So basically, you can run this multi-hop backward forward gene on a graph. So bisect is a very simple schema, but essentially try to completely split the input output coming edge so that you can later simply calculate the representation for each directions and formulate your final node representation. The second one called bifuse. Bifuse by name is try to fuse the intermediate representation from both incoming and outcoming in order to achieve, do this fusion step a little bit early. So in order to do that, so we found that so this is sometimes will perform better, sometimes perform worse compared to bisect. We'll have some experiment later, but this is essentially another way to do the bidirectional graph neural nets. So the graph encoding part is, as we mentioned, right? So you already compute that node embedding for each graph node, and later you have to generate the graph level embedding so that we can fix as a context vector for the decoding part. So there are two ways to do that. One is a pooling-based graph embedding. Here you can use like max pooling, min pooling, or FG pooling. Another one called node-based graph embedding. So here you just try to insert a super node into a graph and use this node to connect to all the other nodes. Therefore, so you can just run this graph nodes or any graph nodes method to generate a node embedding for this super node. And you can use this super node to treat it as a graph level embedding, right? So, however, we have been compared the two methods, found that so seems like pooling-based graph embeddings perform better. Probably the partial reason is that so the node-based graph embedding is really arbitrarily or superficially insert a node into the graph structure that actually brings some noise into the original graph structure, and therefore that is may lose some information. So this is attention-based sequence decoding. So for people who are already familiar with this type of method, it should be very familiar for these terms. So, but essentially, the context vector is using to compute the weight compared to each of the graph input, and then to use a weighted average to recompute the new context vector and use that to decode the token. And the whole objective function here is trying to maximize the probability of giving what token existing decoded what token and also the graph input. So here's some experiment to showing that so this is really working well. For example, compared to other graph-based method and a sequence model, for example, like LTM method. And so we have been testing this on some like baby. Baby is one of the most difficult text reasoning dataset that proposed by Facebook around a few years ago. And so they require, so left-hand side is to give a most difficult subtask in this dataset, and try to show you that once you have all this information, you have to based on a question and then to give an answer. Okay, so in order to do that, so you first transform that in the graph format and then to generate a final answer. At the same time, we also perform the task on the shortest path task that try to find the shortest path between the original data point to the destination. And S means that this graph is a small graph, L is a large graph. Of course, the smaller graph is the easier this task is. So we can see that so for all these tasks, so our graph to sequence model can perform much better to a sequence model and also compared to other graph-based methods. So the reason is very simple, that because that it's a bidirectional node embedding really help a lot. So this kind of a further study about compare the bidirectional node embedding compared to unidirectional node embedding. So we can see that so when the hop size or layers increase, the accuracy each of the method increase significantly. But the bidirectional node embedding method always perform better. That's really because that it can learn the information from both sides. But at some point, so once you each algorithm have reached the context for the full graph, therefore that finally the performance will converge to the similar side. So okay, so by this, so we want to analyze. So when we show you quantum sequence model. So the first case that when you input, right, is naturally represent or best representing graph. For example, one of the popular task in the NLP is AMR to text. So in this case that your input will originally already represent in graph, for example, AMR graph. And then right now you try to generate a text that to summarize. So what is the AMR graph talk about? Okay, so this is example here. So in the second case that this is probably more common case that you have given a text input. For example, here is there any job outside Austin, and now you can augment that with a dependent path tree. So this type of the graph structure we already introduced a lot. So I'm not going to discuss anymore. So, but moving forward, right? So it's, we consider the input side become a complex structure from the graph structure. But in many NLP tasks, sometimes the output side is also complex. For example, the logic form. For example, the math equation. So for this type of the NLP task, the output side essentially is not a simple text. It's also some kind of a structured output. So in this case, so how to bridge the semantic gap between this humanly readable word and machine understandable logic is very important. Semantic parser and the math word problem is just one of the typical applications that we introduced here. So in the right-hand side table, you can see that so this example for the semantic parser is an example for the math word problem. Especially for the math word problem, this is a growing interest in the community. So this is probably the most common thing when kids, right? You see all kind of math word problem. You give a text description about some kind of math thing, and then you have to think about that and give a math equation and then to solve this equation. Okay. So so this is the way that we can do the graph tree construction. Just to show you some of the example, you can use dependent tree augmented the test graph or convolutional tree augmented test graph. In the right hand side, right, you can to decompose this sequence equation into the tree structure. Okay. So of course there are several ways to do the tree decoding. You can use the DFS based tree decoding or use the BFS tree decoder. So this is the model later we propose called Graph tree model. So the first part will be very similar to the graph sequence model, but the key innovation from the right hand side. So instead to use a sequencing decoder, right now use a tree decoder. But one more thing to mention here that it's very important to think about that. So when you construct this graph, right, essentially most of the time is a kind of like a historic graph. That means that the different node may have a different type. So it's better to doing this separate attention to attend each different type of graph node, so that you can learn a different kind of semantic information from there, and then you can doing this tree decoder. And when tree decoder, we also have some innovation. For example, previously only consider parent feeding, but we also propose this sibling feeding that will also help a lot. This denoted by this blue color to the decoding process. So this is a more math part about this separate attention-based tree decoding and how to do the compute the context filter, how to compute the separate attention weights, and finally to generate the final attention hidden state. So this is the experiment result that we have been performed. We can see that compared to all the step art method, so on the different math word data set, the graph tree model can significantly outperform the existing method. But one more thing I want to mention here is that you see some other other method here. They are doing some very specific trick. For example, they are doing some kind of like called equation normalization trick. So this trick I don't like it because essentially, when we do the math word problem, right, as a human being, different person may come out with different equation for the same problem. Okay, but all of them are correct. Okay, this equation normalization trick is trying to normalize them in the same format. So therefore, that you are not able to recover the original reasoning process of the human being. But with our quadratic tree model, we don't do any kind of pre-processing, just directly to decode what we see in the training samples. So I think this is a very important part, because this is really kind of recovering the original reasoning process, or in other sense, it's more explainable. Okay. So this is kind of a realization for the separate attention. We can see that so with the quadratic tree translation, the different attention really captures a different key part of each graph node. So for example, this is attention for the word node, this is attention for the structure node. I can see that it's able to find the most important the token in a different part. Okay, so with that, I'm going to close the first part of this session. We will have a 10-minute break. But if you are interested about the demo session, so the demo session will in the second part, we will first introduce the graph and NLP application. So we will talk about many applications that we have introduced. The Han and Yunyao and Ban will talk about how to leverage the power of the graph units for many NLP tasks. Okay, and after that will be a demo session. So you can prepare for the demonstration by clone this GitHub and install the graph NLP library and try how easily you can use that. Here we also have some reference. If you want to take a look, you can take a look later. Okay, so let me stop here, and in 10 minutes we will come back and talk about various graph and NLP applications. So at the same time, so if you have any question, please ask in chat, and we will try to answer your question in text. And also later we will have a dedicated QA session in the end, and then you can unmute yourself and ask questions directly. Sorry, is anyone talking?
Hi, Linfei.
Oh, hey. Maybe I just stop sharing and then sharing.
Sure, sounds good. Can you see my screen okay?
Yes.
Okay.
Okay, maybe you can kick off in 1 or 2 minutes.
Sure. Hi, I see your daughter in the background.
Oh, yes, I try.
She doesn't have school today?
This week is a winter break.
Oh, winter break.
Yes,
Nice.
yeah. Happy to
We're
kids.
going to have a spring break soon, in 2 weeks.
For university, right?
Yeah, and also for elementary school. Yeah,
Oh,
they
yes.
try to sync with the university. So.
Oh, that's right. Yeah, I believe they also have a spring break. Yeah.
I remember seeing her many years ago. She's very big now.
Yeah, kids grow very fast, especially when they grow up from 6 to 8, something like that. So you feel that they grow very, very quickly, and even their looking is change a lot.
Yes.
Yeah. Okay, I think we can get started now.
Okay, cool. Okay, hello everyone. So I will kick off this application session with the information ingestion, because information ingestion naturally fits into the graph deep learning. And so I will tell you why we are excited about this learning from graphs for information ingestion, and hopefully convince you that this is an exciting topic to work on. By the way, I would really love to get some questions, so because usually it's very depressing to give a presentation to just a computer, without any feedback. So please interrupt me if you have any questions or comments. With any, format you like, you can raise your hand, or you can put your in chat, or you can just speak up. Okay, so I will talk about why we need graph deep learning for information ingestion to improve the quality, and then talk about it's necessary to improve portability. And then I will also cover several new problems created because we used the graph deep learning algorithms. So the point here is this kind of line work is not just helping us do hill climbing, improving the performance of a traditional problem, but it can also open the door to many new and exciting directions. So information ingestion is a task to construct a graph from an input sequence. So the sequence can be a document, can be a corpus, can be a sentence. And when we say graph, we mean the information graph, which means we want to find the most important nodes, and usually they're entities or events. And then we want to figure out their connections, their relations. So the output is a graph. So the conventional way to do this using deep learning is to simply do a sequence to graph conversion. So basically you encode a sentence as a sequence, and then you decode the graph from the sentence. So you probably can see there are several limitations here, because usually the input encoder only looks at the flat structure sequence of words. So it basically ignored all the structures, internal structures, graph structure among these words. And also in the decoding phase, normally we just scan the sentence from left to right using bin search. So we'll miss a lot of good candidates. And also it's not very efficient to capture the long distance when we are doing decoding. So because of these problems, recently there are some attempts to try to address the challenges by incorporating more graph structures. So this is a work by Liu Yang et al. Last year in ECHO. So they try to convert a input sequence into what they call a span graph first. So the idea is to simply look at every possible candidate of trigger, event trigger, and entities, and construct an initial span graph by looking at all the possible connections among these spans, and then encode the graph instead of the sequence, and then do the graph decoding. So in spite from that, at the same time, my student Zixuan Zhang had also a NACO paper. It's also about graph-to-graph encoding and decoding. So the only difference here is instead of constructing a span graph, we are trying to leverage the existing symbolic representation, such as semantic parsing. So abstract mean representation is a special way of getting the semantic graph of input sentence. So you can think of this as a combination of semantic labeling, independent parsing, but it includes a much richer labels for these edges and the nodes. And there's a data set there, and there are many AMR parsers you can use. So we can convert a sentence into an AMR graph that will look like this. So if you look at this graph and compare that with our ultimate goal of extracting this information graph or information network, information graph is really just a subset of this AMR graph. So that means if we can figure out which subset in the AMR graph is important one, then we can simply convert this problem into graph encoding and graph decoding. Okay, so that means in addition to the input sequence, we can now leverage the AMR graph from the input sequence and then use the graph encoding to have a much more reliable representation for every concept in the sentence. So the basic framework is following the graph attention network that we have already seen in the previous sessions, especially the edge conditional graph attention network will fit this problem really well, because usually our the graph input AMR graph is a heterogeneous network. So you can see what we are doing here is we first initialize the node embedding with their regular word embedding, and then use the then we update every node representation using edge conditional GAT. In this way, we can effectively incorporate all the information from all the neighbors from each node and do message parsing through the graph. So, so that's about encoding, and also for decoding, since now we have this AMR graph serving as our intermediate representation, now we can do decoding in this graph instead of sequence. So why that's important? Because sometimes you will see an event trigger and entity that are far away from each other in the sequence, but in this graph structure, they are maybe just neighbors, because the graph structure can help us compress wide contact. So the idea is let's do a top-down decoding instead of left-to-right decoding. So we'll start from the root node, and then once we find a trigger node, event trigger node, for example, a trigger that indicates attack event, then what we can do is we can simply look at all the subtree or subgraph covered by this node to look for the entity candidates associated with the event. And then in that way, we can just ignore all the irrelevant subgraphs and do this decoding much more efficiently, and also capture the long distance contact. So just give you some examples here to compare the sequence to graph and the graph to graph framework. If you look at the first example, the trigger here is airlifting. So this is trigger, and Washington is supposed to be a place argument or attack argument for this airlifting. Right, so this should be playing as agent role. But because Washington is a little bit far away from airlifting, the input sequence, the sequence to graph framework failed to identify this link between airlifting and Washington. But using graph to graph encoding decoding, we can find this link back. So that's about improving the quality. And then graph structure also provided us as a nice common language or intermediate language to connect multiple data modalities. So there has been a lot of work about how to use the structure to represent multiple languages. So I'm not going to talk about that because there are a lot of other tutorials already mentioned that line work. So similar work will be multimedia representation. So again, there's a lot of work working on multimedia representation, how to consider image and video as a foreign language, and we can find a common semantic representation between image and text and between video and text. However, most of the existing work ignore the graph structure inside the video, inside the image, and align the information on a structure level. So if we take a close look at most of the images, for example, in news media, we often can see some interesting structures. For example, this picture will show us there's a movement event, and we can see this is a vehicle. This object placed as a vehicle or instrument or artifact, this kind of role in this movement event. So how to represent this more precisely, we can leverage this kind of semantic graph to figure out the situation of this image, and then align that semantic graph with what we can extract from text side. So let me give another example. So here in the image side, we can see there's a throwing or tag event, and we can see this is a person who's throwing the stone, and the stone is the thing that's being thrown toward some target. So in addition to the basic, pixel level or bounding box object level alignment, we can also convert this image into a graph structure, such as a scene graph or a situational recognition graph, in which you will have a root node that is showing you the event type, and then also the object and their roles play in this event. So the usual data set for object detection won't be able to cover all the concepts. So what we can do is we can also just use implicit representation for those objects. For example, we can use attention map to represent these important entities, and then convert this image into a semantic graph, which will look like this. So we can see from this graph, the labels of these nodes and edges now can serve as a common language to connect image and the text. So we can see, although we don't know the event type for throwing, but the throwing is semantically closer to a tag node from this caption sentence. And similarly, this man, this agent, is also similar to the agent role in this attack event. So in this way, we can align the semantics not just on the sequence or the image, raw image level, but we can also do that on the graph structure level. So we use BioLSTM to encode the original input sequence, but then use graph convolution network to encode these two graphs. And this common language labels serve as bridge to connect these two graphs. So why that's powerful? Because once we do this, then we can simply encode millions of image and the caption pairs, or maybe millions of video and the speech transcript pairs into this common semantic space. And then once we have any training data, either from the NLP side or computer vision side, we can use this common semantic space to represent them, and then we can train a model or even a joint model by merging all the training data from multiple data modalities. So here, this one is the text side of training data with manual annotation. This one is the situational recognition corpus, also manually annotated, lots of images. And then we can use our common semantic representation to encode both, and then train a joint model. So let me see if there's any question here. When building the graph, do you need interaction adjustment from human being? So far, all the examples I'm showing are automatically constructed. So yeah, so there will be some noise, and sometimes the graphs are very incomplete. So there's some ongoing work in terms of an interactive way of constructing semantic graphs. So I didn't include any deadline work here, but if you have interest, we can follow up. I can send some references and can have more discussion. Okay, so that's about improving the portability, because you can basically merge the modalities using the common graph structure and then transfer the training data from one data modality to the other. So I'm showing you a couple of examples of output examples to show why merging multiple data modalities can help. So for example, here, if we don't look at the text side, we may mistakenly identify this as a protest event because of a crowd. If we only use image system, but using the common semantic representation, we'll be able to successfully identify this as a play. So it's a happy play instead of protest. And similarly, on the right side, if we ignore the image side, we may mistakenly miss this arrest event because search is not a common trigger word for arrest. But looking at the scene graph and the situation recognized from the image side, the graph structure, we clearly know there's an arrest event going on. So that's why the joint model can extract this kind of additional events and structures. So compared to the existing cross-media flat representation, so when I say flat, I mean they are aligning objects with the words, aligning pixels with the characters, but they didn't really look into any graph structure. You can see using a flat representation, sometimes we can identify the event, but the role will be incorrect. For example, this man will be mistakenly identified as agent instead of entity who is being arrested. And similarly, when we have a bounding box, which includes multiple entities, the flat representation often made a mistake, either missing the role or assigning an incorrect role. So that's another example about improving portability. I also just want to mention that the whole NLP community, I mean, most methods are kind of limited to sequence, right? Just because it's convenient for us to leverage controlized embedding that way. However, if we try to take advantage of the graph structure, we can actually take advantage of much more global knowledge. So I would like to give a quick example in that regard. So in the sequence to graph framework, it's extremely hard to encode any global constraints because you basically consider every sentence as a unit, as input. However, to do a lot of NLP tasks, we do need a lot of background knowledge, global knowledge for us to do reasoning. So one example is, again, event injection. We often need to understand what are other events that cause this event so that we can know who is involved. So it's really important to induce this kind of event connections. And we usually call this as event schema, which means the skeleton or the templates that connects multiple events under one scenario. So this is a schema example for civil unrest scenario. So you can see under civil unrest, there are 3 big events, big chapters. So the first chapter is coup, the second one is international intervention, the third one is ceasefire. So this is actually what we can see this week from the Ukraine-Russia news, right? So you can clearly see these patterns. So the same pattern has been followed by previous articles or historical events in the past. So the idea is if we can analyze this kind of patterns automatically, induce this kind of graph structure automatically, we can translate them into global constraints or features to help us do better job in information ingestion or other NLP tasks. So to induce this kind of schemas, we can use the graph generation model that has already been mentioned in the previous sessions. So the idea is, if we can gather together lots of instances from the historical data, we will find on the type level, they always follow similar structures or patterns. So for example, this is about a schema for a bombing event. So usually the attacker will go somewhere to learn how to make a bomb, and they will buy materials to make a bomb, and then they put it somewhere, and there's a detonation event, and then some people will die or got injured. So if we know this, right, this kind of schema, then we not only can extract events, we can also predict what's going to happen in the future because the history repeats itself, the graph structure repeats itself, so we can induce the graph level patterns. So what we have done is we try to design a generative event graph model. So we will start from a few seed events that we already observed from the existing articles. And then we will let the model to predict what's going to be the next event. So arrest appears most frequently as next event after attack. And then we can predict what is the most frequent edge connecting attack and arrest. And then further, we will try to identify the temporal relation between these two events and analyze the roles for these entities played in each predicted event. So the idea is you start from what you know and then grow the graph to cover future events. So we compared this kind of output with the human prediction results. So human prediction means they will use their own knowledge, and they will construct a schema from scratch based on that knowledge. So we can see the prediction results are much better than using human schema, because human is not good at producing multiple hypotheses with a different uncertainty estimation, but such a statistical model can give us a very reliable estimation about what should be happening in the future with what kind of probability. So for example, here, human schema mistakenly predict trial hearing, this kind of event. But this person was not arrested yet, so it's impossible to have a trial hearing. And our automatically induced schema can successfully identify or predict the next events right after the current chapter. So that's about schema level prediction. But the much cooler thing is we can actually also do instance level prediction, which means we can look into the original graph structure. We not only predict what type of event will happen in the future, we can also predict who is involved in what kind of role, who did what to whom for this future event. So for example, if we don't have a child and a sentence this event in the input article, we can then predict the whole chapter, and then we can also propagate this entity because this person has been involved as a target for investigation. So we know this person is likely to be the entity that should be charged, should be convicted, and should be sentenced. So you can see that's really, opening up some new directions to go once we have the graph structure. And I just want to mention a couple more other new directions using graph structure. So once we have this kind of multimedia information graph constructed from natural language and maybe images and videos, we can also do multimedia and multi-document summarization, such as timeline generation. So timeline generation will require us to look into not just the, which events are most important, but also sort them into a timeline. So this is a paper based on collaboration with Binfei and others. So we first converted the input documents into a very big graph, and then we can do graph compression, and then using the graph to text generation, using this graph compression as a condition to generate a timeline. Or if you don't want to do generation, you can also simply select all the sentences that cover the subgraph as a final summary, as a final timeline. And this is another application, actually is published here at the main conference. It's about question answering using multimedia knowledge graph. So multimedia question answering is a very challenging task because it usually needs you to do cross-sentence reasoning, look at the whole document, and also do cross-media reasoning. So if we have that cross-media common semantic structure that we mentioned, then the task becomes much easier, because when you are searching for the answer, you not just look at the words and the phrases or maybe bounding box in each image, in each sentence, you're actually looking at the multimedia knowledge graph that you already constructed and use that to find the precise answer. So we found that this multimedia information graph helps dramatically about the QA performance compared to sequence and a flat model, flat representation. Okay, and then I want to mention another application, which is, personally, I think is a very exciting work because it can change the horizon of what we are doing in terms of combating fake news. So the existing work about fake news is we just look at, for example, whether any sentence or any word fits into language model. Right? If the word looks weird in this language modeling context, then we think that's fake information. But that's not how human would judge whether something is fake news or not. So I would like to start with a quick quiz. So you can let me know which one do you think is fake, the left one or right one, by reading these two articles. In the meanwhile, Jen has another question. Do you have the KG ontology in your yes, so for all the work I have described so far, we follow some predefined ontology, and I believe we have footnote in the paper as a reference to the ontology. If you cannot find it, you can shoot me a quick email and I can share with you. Yeah. So yeah, so because they are still kind of supervised models, right? Because once we have the multimedia representation, we still need to train the model. So that's why we follow some predefined ontology. But in the community, there has been a lot of work on how to discover the ontology, for example, how to do zero-shot learning, you have to type. Yeah, so I didn't cover anything on the OpenIE side, but there's a lot of work going on there. They did not use as much graph as we do because the philosophy there is try to not use sophisticated linguistic structures or resources. So yeah, but if we want to have very high quality IE output, we do need to leverage graph structure. That's just my personal opinion. Okay, anyone wants to make a guess which one of these two is fake? You can type your answer maybe in chat. So Jim, since you are the most active on here, do you want to make a guess? Is left or right one? This is a news about what's happening in Burmese news article about Aung San Suu Kyi. So if you are not following Burmese news closely, it's probably very hard to tell which one is fake. So the red part highlights the difference between left and right. Okay, for the interest of time, maybe I can just tell you the answer. So the answer is the right one is fake because all these red highlighted knowledge elements are fake. So this relation is fake, and the events is Howie, yeah, you're correct. The right one is fake. So you can see from just language modeling features, it's really hard to detect this kind of fake information. The reason they are fake is because they don't fit into the story, right? So they don't fit into the knowledge graph or the information graph we can inject. And similarly here, these two captions are for the same image. And because of interest time, I'll just tell you the answer. So the left one is fake because these troops, they just arrived, they are not leaving the facility. But if you have never been to this place, it's really hard to tell this is entrance or this is exit, right? And here, similarly, the only difference is the location. One says this is Milan, the other one says it's Berlin. So if you can recognize the street scene or maybe this, the foreign language brand names, then maybe you can tell this is in Milan. So the Berlin one is fake. So that's why I'm saying we are not really relying on language modeling alone to do fake news detection. What we have in mind is actually something like the multimedia information graph that I already mentioned. And then we try to analyze every node and every triple in this graph to see whether it's fake or not. So for example, here, all these concepts are true, right? So you do see police, you see this location is in Hong Kong, there's a crowd, but then the role this police played in this attack event is inconsistent between the image and the captions. So the caption basically saying they are shooting at the protesters, but the image did not say that. So what we can do is instead of working on sequence level misinformation detection, we can first construct such a multimedia knowledge graph and then try to analyze every knowledge element, every triple or every node and every edge to see it's true or fake. So in this way, we can detect fake news in much more accurate fashion and also make it more explainable because we can tell people, which knowledge elements caused the fake information. So the task simply becomes looking at every triple of two nodes and one edge and determine that's as a fake or true information, and then using that as features to determine the whole document is fake or not. And the cool thing about this is we can now also aggregate knowledge from multiple data modalities. So for example, we can link this bounding box with the place, and also maybe link some events across image and image caption articles. So we can have a multimedia knowledge graph, and we can propagate our evidence across these different graphs. And then we can use that as a final representation of every node and edge and do the classification. So one more bottleneck about this task is we don't have any training data, because human written fake news is usually removed immediately after they are published. So we will need to figure out a way to automatically generate training data. And again, graph plays a really important role here, because if we can manipulate the knowledge graph somehow so that it can become a slightly fake graph from the authentic news article, then we can generate lots of training data for our detector. So basically the idea is, given a set of real news articles, we can construct knowledge graph, and then we manipulate the nodes and edges using all kinds of operations so that we can generate a fake knowledge graph. And then we use that graph to condition our natural language generation to generate the training data. So the operations we have tried include entity swapping, which means we will replace the entity with its most similar one. And we also will add some new relations and events. And sometimes we can even replace the whole subgraph with another subgraph from another article. So these are just some examples. So one thing here we need to notice is that if we simply replace all the entities, we might generate a too easy document, which means it's really easy for human or machine to detect. And we don't want that kind of training data, because if you train a detector from easy training data, your detector will not be robust to detect the difficult ones. So we try to avoid that by not touching any entities that are already grounded in the images. So for example, here, if we replace bicycle with a truck in a knowledge graph, then this detector will not be able to detect this if it's trained from this kind of data, because this bicycle is already appearing in the image. So using the cross-media consistency checking, we can easily detect this truck as a fake information. So we don't want that kind of fake information. So instead, we only manipulate the entities which are not grounded in images, such as Zambia, and we replace Zambia with the most similar country name, Fiji. And then we generate a fake article that will look like this, and use this to train our detector. So this opens up the door to do condition knowledge graph, condition generation. And of course, it highly depends on the quality of the knowledge graph. So we want to further improve the coverage and the accuracy of these knowledge graphs. So we also can try other type of ways to construct a graph, for example, AMR graph. So these are other operations we did on the AMR graph. So we switch the roles, and we sometimes also do negation, which means something happened and we change that to negation did not happen, or something did not happen, we change that to some event that already happened. So this kind of training data can help us improve the detector significantly. So these are some results we are showing compared to the existing tool techniques. So Grover is a language model only based detector. Didani is multimedia one, but they did not use multimedia knowledge graph. So you can see our detection accuracy is much better. And also it's much more explainable. For example, here we can detect this as a fake document and also highlight the knowledge elements which are fake. So this is not Twin Towers, this is another facility. Okay, so that's all for my part. Just want to quickly mention, we also make everything available, public available as source code and Docker, and also on GitHub. So this will include the IE system itself and also the demos. And the IE system includes multilingual, multimedia, and multi-document, and end-to-end pipeline. And we're also actively updating the quality of every component. So everyone is welcome to use. Thank you. let me see if I have another question. When generating language condition on graph, is there a common usual procedure followed? Does it make sense to use node embedding with the pre-trained language? Yes. So for the first question, yes. So usually the graph serving as knowledge constraints, and basically, let me see if I have anything talking about data algorithm here. So, okay, let me maybe just go back to the graph example. So suppose we have this graph, right? And then we change this edge, for example, to, instead of say this is a shooting, for example, we change the Hong Kong police with maybe, maybe students, right? Then in the generation, we'll make sure the output, the sequence output include those manipulated knowledge elements. So the language modeling in that condition generation is really just trying to stick the pieces together. So we already have this fake knowledge graph, and we just want a generator to describe the fake knowledge graph. So there are many different ways you can do that. For example, you can simply use copy mechanism, or maybe you can add attention weight for each node in the, if you want to emphasize the fake part, you just use that. So for this work, we simply use a BART model, but conditioned on the graph. So we linearize the graph into sequence and kind of convert that sequence into the final description. And this can be trained from any graph conditioned generator, trained from other data sets. I hope that answered your question, the first question. And the second question, yeah, so that's exactly what we did. So each node here is initialized by its own embedding, right? So for this work, because we are looking at multimedia, so this node is initialized using the multimedia embedding that I mentioned. And then once we have this cross data modality graph, we can then do message passing across these graphs so that we can update the nodal representation. Yeah, so I think,
go back to the page.
Yeah.
126.
Sorry, can you repeat?
Yeah, would you mind go back to the page 126?
126, okay. Yeah. Is this one you're referring to?
Probably one more. Sorry, I remember the wrong. Yeah, this one.
Yeah.
So like so your input is the document, and how do you can you provide more details? How do you build this knowledge graph ontology? What do you just how do you starting with it?
Yeah, so for these input documents, first of all, we assume they are about one complex event. So we need to do some sort of complex event clustering first, right? So for example, these are about, I don't remember, this is about what, Michael Jackson's event, I think. Yeah, so we need to group the documents first. And then for each cluster, we'll do entity relation, event ingestion, and also event template ordering, right? So all of this construction part is done by the sequence to graph or graph to graph model that I mentioned at the beginning, right? And we do have annotations to train those models, and the annotation follows a predefined ontology. Does it make sense?
Yeah, so the starting position here at transport, so their class or the instance? Their class, right?
You mean these input documents?
No, I mean in the knowledge graph, which one are you showing, the class level, the knowledge graph, or the instance level?
Oh, so for this work, these are all instances. So you can see, for example, this person we know is Michael Jackson, and Michael Jackson is playing a semantic role called employer with the start position, and the start position is triggered by this word called hired. So hired appears in the input document. So this is an instance graph.
Okay. So do you need to pre-configure the class levels first, and then like how do you generate this graph? I just want to know more, a little bit more.
Yeah. So yeah, I see where it's confusion. So we have a predefined ontology. So the ontology will say, I want to look for the following types of events, start position, transportation, and so on, right? So that's a task, right? And then it will also say, for each event, you need to identify this kind of roles. So when we do the sequence to graph or graph to graph information injection, we're not only identifying the entities or events boundaries, we also need to assign them to those predefined class, or what do you call as class or type, right, in ontology. So does that make sense?
Okay.
So, yeah, so like when we see the word hired, right, we not only need to know that's the event, we also need to know what type of event it triggers. And then when we see Michael Jackson appears in the sentence, Jackson, right, we also need to know that this Jackson has a connection with the hired, and the role is an employer.
Right. So when for example, you have a class as a person, and you can assign the Jackson as a person, right, into that class. But how? And you have some activities: born, injured, die. You have that the vocabulary.
Yeah.
Identify this identify the class, right?
Yeah. Yeah. So yeah, so that's why I commented that this whole graph idea is now still more suitable to this traditional supervised model kind of IE framework, just because we can provide such rich typing information, right? And this is usually really very important semantic representation from nodes and edges. If you just look at OpenIE, usually you get a dependency parsing output. You don't know the type of the events, you don't know the rows, so the graph won't be as rich as what we are seeing here. But of course, the trade-off is the quality is limited. It's not covering, the whole world. So, the ontology is also predefined for some certain scenarios. Yeah. Okay, I think I'm running out of time, so I should stop here. But, everyone is welcome to follow up with any questions or comments on chat or by email. Thank you.
Thank you. Appreciate it.
Lin Fei, I forgot who is next.
Yuan is next. Yeah.
Okay.
I'm in the next, right? So
Yeah, that's right. Yeah.
Yeah, but I cannot share screen. Okay, now I can. Okay, never mind. Can you see my screen now?
Yes, we can.
Okay, great. Okay, so the next application I'm going to talk about is machine reading comprehension. So just a very brief introduction for the task. Machine reading comprehension is the task of giving a question in natural language that can be answered based on unstructured data and or semi-structured data, extract an answer or select a correct answer from a given list. One particular type of challenging type of task in the machine reading comprehension called the multi-hop reading comprehension, where the answer can only be obtained based on reasoning across multiple documents. So one particular popular data set for the task is called the WikiHop. So here we basically, the input is a question in the form of source entity relation unknown answer entity, along with a shortened list of candidate entity. Then based on Wikipedia and the Wikidata, the reading comprehension system can select the correct candidate entity from the given list. So this is this particular data set in general looks like. So I'm going to introduce a few work that is using this data set to build models. So the first paper, Cha et al. Is one of the first papers that leverage graph neural network for multi-hop reading comprehension. So in this work, it constructs entity graph with nodes based on mentions from all supporting documents. The nodes are connected with different entity types and relations. So as you can see from the graph here, we basically have 4 types of entities and 4 types of edges. So we have the document edge, actually the ellipses, and then we have the candidate, and then we have the entities. So the edges are the solid, the black one are the document-based one. That basically means the 2 nodes actually co-occur in the same document. Then it also have a dotted line edge that means, you know, these 2 entities are exact match. So this is very reliable way to say these 2 maybe refer to the same entity, but this is, you know, a very sparse way to identify entities that refer to the same thing. Then it also applies some out-of-box coreference model to identify coref relationship between the nodes, and finally introduce another node edge called a complement. So basically for nodes that are not connected with each other, they also have this complement edge, which is not shown in the graph, you know, for simplicity. So once we construct the graph, the graph representation for each of the node is learned via entity relational graph convolutional network using gated version of relational GNC. So you can see the formula here on how to update the vector for each of the node, and then what's the attention gate used, and then how the new node embedding calculated. So the candidate is computed based on the final node embedding as well as the question representation. So this is to use this 2 together to predict the distribution over candidates. So this is the experimental results reported by the paper. So it's really looking into a different element of this approach, what is useful, what is less useful. So based on the results, we can see, first of all, the graph neural network is very useful. If we remove graph neural network versus with it, you can see the drop is pretty significant. At the same time, the numbers also show the previous language model swap from Elmer model by graph. There's some drop, but not so significant. So this means that it's important to choose the right language model, but at the same time, it's not so critical. And then we can also see if we remove relation type, there is a significant drop. That means the relations are very important. And then you can also see the importance of different type of relations. So from the table, you can see, right, like if we remove document-based edge, then we're going to see a very significant drop. The other ones are less important. And especially if you look at the coref and the complement, they're definitely less important than the match one, because based on exact match, that captures the most important and reliable information. The coref may not be as important, potentially not because of the coref is not important, potentially because coref itself is a very hard task. The out-of-box model may not perform as well as it could be to truly reflect the coref relationship. And lastly, the authors also try to, instead of using the actual edges in the document, they try to introduce. So they basically use this heuristic, right? The 4 types to build the edges. So instead of using those heuristics, they replace it with a learned model and introduce those edges automatically. And you can see the introduced edges are not so good. This really means that learning those dependency is a non-trivial problem. So move on to the next slide. So we can see if we increase the number of candidates or increase number of nodes in the graph, the overall runtime, the overall performance drops quite significantly. This is because the graph, with more candidates and more nodes, the graph become more complex and reasoning become more challenging. So the next paper follow up on this one is kind of taking very similar approach. The main difference is in the first paper I just mentioned, it only take entity level information into account. In this new paper, 2 et al., they try to take information from different granularity into account. From candidate, document, and entities, it first generate query-aware candidate, and then document and mention vector representation with co-attention and self-attention. So co-attention enabled the model to consider codependency between query and document, query and candidate and mentions, and self-attention pruning summarize the information presented in the co-attention output by computing a score for each word in the sequence. So as you can see, the heterogeneous document entity graph contains 3 kind of nodes. So we have document nodes, candidate nodes, and entity nodes, and then it also introduced more kind of edges. So if you remember, right, what we discussed earlier, there were 4 types of edges. Here, there's 3 types more. So similar to the previous one, we have, the relationship between entity and entity, whether they're in the same document or they are the same mentions of each other. Then they also have document and candidate, document and entity, candidate and entity, and so on. So basically, the entire graph is richer than what we have seen before. Once the contextual embeddings are initialized in the graph, I get the GCN is used to train the node representation in the graph. So, and similar to what we have seen before, this is a heterogeneous GCN, and then that from this we will compute the graph embedding. So the final node representation of candidates and entity nodes corresponding to mentions of a candidate are used to calculate classification scores. And based on ablation test study, we can see the graph itself is very effective. With and without the graph, we can see a pretty evident job. And then the different edge types are also important. If we remove the edge type, we can see a job. Meanwhile, if we look at it in more details, what kind of node score are most important? We can see entity node scores are most important, and entity nodes are the most important. So this is not very surprising, right? Because most of the reasoning is really based on relationship among the entities. Entity carries the context information in the document, while the candidate node do not carry such information. So then we can also look at the model performance as the number of document or candidate increase. So similar to what we have seen before, performance drop when the graph become more complex. So this is very reasonable because more document means more entity and a bigger graph and more challenging for reasoning. So it's really the same issue. When the graph become more complex, it's just more challenging. Then there is a more recent work. It's again, construct a graph over the original document, but here instead of looking into individual entities, it actually leverages semantic row labeling to construct the graph per sentence. So it's also a heterogeneous document level graph. So we can see the node type of a sentence, and also the sentence include the question, the title, and other sentences in the document, and then using semantic row labeling to construct a subgraph per sentence. Let me show you an example here. So you can see this is how a heterogeneous SIL graph is constructed. So we can see there's the argument node, right? So we also have document level node that include questions, titles, and other sentence. And then we have SRL argument. So in the yellow square, curved edge square, you can see the subgraph constructed based on argument predicate for sentences. And then it has predicate edge. It has edges that contain sentence nodes and argument nodes, and then edges connecting sentence with shared argument based on exact match. So this is basically even more comprehensive graph constructed for the original, for the document and the question. So similar to what we have seen before, this is also construct a static graph. So once the graph is constructed, we don't really need to do much change. So for this particular work is evaluated on another data set called the hotpot QA. And you can see here, this new model compared to the existing work before this work was proposed is much more accurate and improve a lot of the aspect of the model. So one reason the author look into why this model performs better, one big reason is that compared to the previous work, which is mostly based on relationship between entities, using SRL and the relationship between the SRL subgraph is significantly improve the completeness of the graph network to provide more semantic edges to cover reasoning paths. So we can see the additional ablation study. So if we remove the graph, there is a significant drop. And then if we remove the argument type and the semantic edge, we also see significant drop. So you can see basically the two key components, right, in this particular model are both important. Both the SRL graph is important, and then the details of the subgraph, the predicate edges and argument type are also very important. If we remove those, we will break the chain of reasoning, and that lead to the significant drop of quantity. So the main source of error is quite interesting. I think this maybe can give you some idea of if you want to build your own model, right? What are the things to watch out for? So this is based on error analysis that the authors have done. So you can see the like 6 different type of main error. The first 2 actually are the most common one. So we mentioned, right, when we connect the subgraph across the sentences based on SRL structure is based on exact match. So as a result, you can think about if 2 nodes, they are not exact match, but they are synonym or slight minor linguistic variants of each other. In this particular work, they are not connected with each other. And that will lead to a drop in terms of coverage, right? Then the other kind of the more of a precision issue, like for month and year number, even though the value are not related to each other, but because of the same type of temporal argument, they're somehow related to each other. Then there are also missing edges that can only be added when you have external knowledge and so on. I think there's a lot of the room for improvement, but the basic idea is that based on the work we have seen so far, right, the quality of the graph matters a lot. Like the more we can improve the quality of the graph, then the more likely the graph will improve the downstream task for machine reading comprehension. So I see some questions here. Okay, so maybe one question is about dynamic text graph construction. I think maybe anyone has input on this. I don't know, like what's the average number of words required? Yeah, I will mention one work related to dynamic text graph construction, but I don't really know a number off the top of my head. Linfei and Yun, do you have any thoughts?
Yeah, for dynamic text graph construction, what's the average number of words required? So this is really depends on the input. So basically, the number of the word is come from the given text input. So for example, once you have a sentence, right, you can tokenize them into the word token. Then if you use this sentence to construct a dynamic text graph, then it's just using the number of the word token you have. So if you're using a document, then it, that means that so afterward you just using the number of the word token in a document as a graph node. So it really depends on the applications.
Right, but I think that is more. I think for static graph, it can be significantly larger. But I think for the tasks that are using dynamic graph, right, typically it's not going to be as big as the one we use.
That's right. Yeah, typically it's smaller. Yeah, typically just using the word token.
Yeah. Okay, so maybe let's move on. So we talk about machine reading comprehension, and one particular interesting work I want to bring up here is a textbook question answering. So this book contains, so you can think of, instead of reading individual document, so the textbook question answering is the supporting question answering over individual books. And the books compared to typical textual document with we have in the task, it contains visual content as well as textual content, so required to solve multimodal QA problem. And also the questions themselves can contain text related and diagram related questions. So it has additional challenges on top of what we have seen earlier. So you can see some example question here. So the key challenges is multimodality. The second is long context. So as you can see from the chart, right, the average length of context for textbook QA is a few times larger than what you see in the more popular question answering task. And then it's also more difficult to solve on same problem because typically each of the textbook cover one subject, right? So if you have additional problem, you probably need to read another textbook to answer those problems. So let's see, how this particular work solve all those challenges. So the first, so you can see that this is the overall architecture of this particular work. So it contains two steps. One, the first step is preparation step. So the preparation step is to find the case answer among n candidates. The context is determined by TF-IDF score with the question and the case answer. Then the context is converted into a context graph. The question and the case answer are also embedded by graph and character embedding. So this step is repeated for n candidates. Then the embedding step using RNC as a sequence embedding module and GCN as a graph embedding module. So with the attention mechanism, so we can obtain combined feature, and then after concatenation, and the fully connected module can predict the final distribution in a solving step. So this again, it constructs a homogeneous, for each of the graph constructed is a homogeneous and is undirected. So that can just use the GCN to create the graph embedding. So the text questions, as we mentioned earlier, right? Text questions are very domain specific and very difficult to use training data over certain kind of a textbook or certain connection of textbook to help predict unseen question. So this work introduced a step called self-training to help the module learn to read and understand a textbook and problems in advance without help of a teacher. So on the high level, you can think about it, it's almost like how human beings learn to answer questions in an exam, right? So even though maybe you did not attend the course, at least you can read the textbook on your own, and then that will allow you to perform somewhat better than not study at all at the exam time. So here it's the same idea, allow the machine to read and understand the textbook and the problems in advance, assuming TF-IDF is retrieval reasonable candidate for the question answers. So this is a adolescent study. So with the self-training, you can see the different way than without a self-training, right? So with self-training, even just over the training data itself is useful, and then construct the context graph is very effective. So basically, both the element, right, the part of constructing context graph as the element of self-training are both important. And you can see the model performance number is much lower than what we have seen before for other machine reading comprehension tasks. So this really clearly shown this is a particularly challenging type of the reading comprehension task. So I think maybe we can spend a bit more effort on this kind of challenging task in the future. So there was a question about the dynamic graph. So here I'm going to introduce one particular kind of task that actually involving dynamic graph. So this is the conversational machine comprehension. So conversational machine comprehension is to answer a question in a conversational manner. So given a passage and previous question answer pair, find the actual answer. So conversational task is much more significantly challenging, and in general, there are two major challenges. First of all, the topic of focus usually shift as a conversation progress, so making it difficult to actually model the conversation. And also many questions later on actually refer back to conversation earlier. So without the model needs to really utilize the conversational history to correctly understand that question and find an answer. So you cannot really deal with one question independently at a time. So this is architecture of the proposed framework, consists of an encoding layer, reasoning layer, and a prediction layer. I'm not going to go into a lot of details for each of the layers. So let me focus on the reasoning layer, which is the most interesting part. So as you can see here, it has the context graph learning component that dynamically construct a question and the conversation history of it, where context graph at each turn to model semantic relationship among words, and then apply GCN to process a sequence of context graph. So this particular module really combines the advantage of RNN, which are good at sequence learning, and GNN, which are good at relational reasoning. So yeah, so this is a summary, like mapping to what we have talked about before. So with the dynamic graph, we can easily visualize the changes of hidden representation of the context word between the consecutive term by computing the cosine similarity of hidden representation of the same context words at each turn, and then highlight the words that have smaller cosine similarity score. So you can see from the figure, it highlighted the most changing context word between each turn in our conversation from the core QA dev set. As you can see here, the hidden representation of the context words which are relevant to the follow-up question are changing the most, that highlighted the most. So this is potentially because as the focus shift, the model found out what's the context chunk that is relevant to the previous term become less important, but then those relevant to the current term become more important. So you can see the changes as the conversation flow. So in general, in machine reading comprehension, graph neural network is very important because it it's a very good way to support mental health reasoning, and also it provides a way to encode heterogeneous information from different granularity, right? We are looking at the document level, entity level, at the semantic role level, and also the predicates and so on. So that's the end of my part. Let me see if there are any questions. Oh, okay, there is no questions. Any more questions before I move on to the next part? I think you will continue. Okay, so let me stop sharing here. So Yue, please go ahead.
Yeah, thanks, Yunyao. Yeah, let me first share my screen. Okay, yeah. So in this part, I will talk about some interesting applications of graph neural networks in natural language generation tasks. So first application, LG task I will be talking about is natural question generation. So yeah, the task of natural question generation aims to generate natural language questions from a passage and an answer. And ideally, the generated question are supposed to be relevant to the given passage and the answer. So the question generation task has many useful applications, such as providing training data for question answering systems. So this ICLR 2020 paper proposed an RL reinforcement learning based graph to sequence model for the QG task. So as we can see from this diagram, so the model consists of a GN-based graph to sequence generator and a hybrid evaluator combining both the traditional cross-entropy based loss and the reinforcement learning based loss functions. So in order to better capture the rich structure information of the in the passage text, so the authors proposed to construct a passage graph which contains each word in the passage as a node, and then they apply a graph neural network to encode the graph. So and for the graph construction part, the authors explored two different strategies, including the static graph construction and the dynamic graph construction approaches. So for the as for the static graph construction approach, so they build a syntax-based static graph where a dependency tree, a dependency graph was constructed. And as for the dynamic graph construction approach, they build a semantics-aware dynamic graph where node embedding based similarity metric learning and the KN style specification were applied. So since we've already introduced like these techniques in the previous part, so I will not go into the details about this. And because the constructed graph is actually a directed graph, so the authors applied the bidirectional GNs to encode the graph. So specifically, they introduced the bifuse GGN as the graph encoder. So as we can see from the experimental results, so the static graph construction performs like slightly better than the dynamic graph construction in this paper, but the performance gap is quite small. And as we mentioned earlier, the one benefit of the dynamic graph construction is that it does not require like prior domain expertise about the data. And we can also find that the bidirectional GN performs better than the unidirectional GN significantly. And we can also see that the graph to sequence model performs better than the sequence to sequence models on this QG task. So the next NLG task I'll be talking about is code summarization. So this task aims to generate natural language sentence which can summarize the input piece of code. So this ICLR 2021 paper also applied the GN-based graph to sequence framework for the code summarization task. So specifically, as for the graph construction part, they proposed to combine the static code property graph and the attention-based dynamic graph. So as for the dynamic graph, they applied a structure-aware similarity metric learning to utilize the edge information of the intrinsic static graph, so which we have already introduced previously when we talked about the graph construction for NLP. So they also So as for the graph representation learning, so because the constructed graph is actually a multi-relational graph, so the author proposed to apply a multi-relational GNN to encode the graph. So specifically, they proposed a hybrid GNN which runs message passing on both static and dynamic graphs. So one interesting finding of this paper is that they tried to combine the benefits of the static graph and the dynamic graph, and their experiments showed that combining these two types of graphs actually performs significantly better than using only static graph or dynamic graph. Yeah, so so that concludes my part for applications of GNNs in NLG tasks. The next, I'll pass it to Bang to talk about text clustering and matching.
Thanks you. I will share my screen. Hello everyone. So now I will talk about the graph representation and graph neural networks for text clustering and matching. So usually when we search about an event in the search engine, or we receive news article recommendations, we will receive a list of documents. So there are several problems with that. So first is we will see many redundant information contained in different documents because they may be about the same event reported by the different news media. And second, we don't know the relationship between different news articles, so they're unstructured. So in the work about the story forest system, we propose to cluster the news articles focusing on the same event into an event cluster, and then we organize the correlated events into a tree format, which we call story tree. So for example, in this, here is about a story tree about the 2016 United States presidential election. So for example, we organize the different events according to the time and according to the coherence. So let's say start from the Trump becomes the presidential candidate until he is elected to be the president. And we have several branches, let's say the different television debates and the mail door of the Hillary. And so here basically the key question is how we can cluster different articles into the fine-grained event clusters. So we propose a graph structure-based two-layer graph-based clustering. So basically we first extract the keywords from the corpus of news articles, and based on the co-occurrence relationship, we construct the keyword graphs and divide it into several keyword communities by community detection over graphs. So basically, we consider each keyword community as a high-level topic. Then we assign different documents according to the similarity to different keyword communities. So we get the first layer clustering. So basically, we grossly divided a document corpus into a cluster of different topics. Then we further consider each article as a news node, and we construct the document graph, and we compare whether each pair of documents are talking about the same event. And in similar way, we construct the document graph and perform community clustering again, so that we get fine-grained event clusters. And after we get the event clusters, we judge whether each event belongs to an existing event in a story tree or it is a new story. So in this case, we append the new event nodes to the existing story trees, or get a new story tree if it doesn't belong to any existing story. So the story forest system is applied to the QQ browser hot topic list in 2017, and now so this is how the product looks like nowadays. So basically, we have a list of different hot topics. So let's say this hot topic is about the Beijing Winter Olympic close ceremony, and if you click on it, it will have show a storyline organized by time, so which contains the different events related to this topic. For example, start from the open ceremony of Beijing Winter Olympics until its close. And this is basically the full line of this storyline. And a recent work proposed called the Fin Event framework. So here they are working on like the social message events. So we have like different events reported by social media messages. And in this work, so they propose like to model the relationship between different social graphs, social messages by a heterogeneous social message graph. So basically the nodes are different messages and the edges, they have different relationship. For example, whether the two message shares the common location posted by the same user or share some common keywords. So in this way, they get the heterogeneous graph. And then they apply like the two-layer, the intra-relational graph aggregation and the inter-relational graph aggregation to get the representation of different message nodes. And there are several threshold parameters which are learned by multi-agent reinforcement learning. And after they get the representation of the different messages, they perform like contrastive learning to let the messages reporting the same event have similar embedding. And if they are reporting different events, they will have diverse representation. And finally, based on the learned message representations, to propose deep reinforcement learning based DBS-CNN clustering algorithm. So basically, with the reinforcement learning, they can automatically choose the two hyperparameters for this clustering algorithm, and in this way, they cluster the different social messages into different event clusters. So for more details, we refer to the original paper. And basically, the system works in 4 stages. The first is like the pre-training. So they have the initial message block, which is like a set of different social messages. Then they construct an initial message graph and train the initial model to detect events. And in the stage 2, which is the single language detection, so they have like incrementally detect new events based on like newly coming message blocks, which is like a new batch of messages, and update the message graph and detect new events based on the incremental new inputs. And in stage 3, like if you have like non-English message blocks, they is using an existing model to map the representation of the message into the English message semantic space and reuse the model trained on English corpus. And in the maintenance stage, which is stage 4, so it will like remove the obsolete nodes and perform continuous learning. So basically in this stage, the main focus is like how we can maintenance a suitable size of the message graph so that we can have like high efficiency in detecting events online and incrementally. So in the experiments, they compare the performance of the fine event framework with different baselines, and in terms of the normalized neutral information, adjusted neutral information, and AAAI. And they performed the experiment in both offline manner as well as incremental detection manner. And in different increment settings, the performance of this new framework has better performance than all the baselines. And next, we talk about how we can do the text matching, both like long document matching and short text matching. Like for the long document matching, you can see that in the story first system, we need to compare whether 2 articles are talking about the same event or not. So basically, this is different from like a pair of sentence matching, because for long documents, it's harder to encode the semantic, and you can like shuffle the different passages in the document and maintain the meaning like unchanged. So we need to like, and also with the increase of the length, the time complexity of matching also increase. So our strategy is like we divide long document into several short parts, and we line the corresponding parts within a pair of documents, and we perform distributed matching with corresponding short parts. So we propose what's so-called the concept interaction graph. So this is an example. Let's say we have a document contains 6 sentences, and we extract keywords. So here the keywords are the named entities, and then we perform keyword clustering to group like correlated keywords into different clusters. So for each cluster, we call it a concept in this document. And then we assign different sentences into different keyword clusters by the similarity. So let's say we have a list of sentence ID if you have like two documents, you will have two lists of sentence ID from document A and document B. And then you can like connect the different keyword cluster by the similarity based on the sentences associated to different keyword communities. So this is what we call the concept interaction graph, because we have different keyword concepts and they have interaction ways based on their sentence similarity. So let's say now we are performing the document pair matching. So we have document A and document B. We construct the concept interaction graph according to what we have described. And then on each node, we have like two lists of sentence subset from document A and B. So in this way, we can perform short text matching on each node. So we can use different matching model. For example, we extract different similarity feature, or we can use a Siamese network where we have a shared encoder for the left part and right part, and we have a matching layer to calculate the matching vector. And after this like local matching module, for each node, we have like a local matching vector. Then we perform graph convolutional network to propagate and exchange the messages between different local paths and get an aggregated vector, which represents the whole document level matching, and we classify based on this global matching vector. So in our experiments, our method outperforms different baselines, and we have some interesting observation. So if we compare these two baselines, basically it shows that if you decompose like the content of documents into several parts, even without considering the correlation, your performance will improve by about like 4% in terms of accuracy and F1 score. And if you further like propagate and aggregate the local matching vector via graph convolutional network, it will further improve the performance by 10%. And the experiment was done on like two long news article matching dataset, which was the Chinese news same event dataset and the Chinese news same story dataset. For short text matching, so in this work, this is for the short Chinese text matching. So they observe that some Chinese words are polysomers and semantic information is not fully utilized. And some models suffer potentially issues caused by word segmentation. So for example, in this figure, let's say this Chinese sentence, it means that his words have some, so this polysomy, so it can mean these words have some exaggeration, or his words have some moisture. And also you can have like different ways to segment this sentence. So let's say these two characters, which if you consider they're separate, it means have some. And if they are like combined, it means they are a bit. So in this way, you have ambiguity in terms of segmentation as well as the polysomies. So basically, in this work, they combine the lattice graph representation to incorporate the different ways to segment the same sentence, as well as incorporate the knowledge from a Chinese knowledge graph, which we call the Hao-Nut structure, Hao-Nut knowledge graph, to incorporate the different meaning of the same word. So for example, this is an example of the Hao-Nut structure. If you have a word apple, it can be the apple brand, it can be the fruit apple. So you have like two sense, one sense for the apple brand, another sense for the apple fruit. And for different sense, you have like different summies. For example, the apple brand is related to like computer, pattern value, brand, and so on. And for the fruit apple, it is related to like the same tree, reproduce fruit, and so on. So basically, in the model, they incorporate these like the possible ways to segment the graph sentence as well as the knowledge. And it takes the embedding from the BERT word embedding and also takes the sense embedding from like a trained model. And then they perform sense updating and word updating. So basically the updating is based on like the graph structure. So in this way, they can exchange messages between different words and different sense. And then they have the character embedding. So the character embedding is also based on the connection between each character and the corresponding word. For example, what does the word contains the character? And they perform like the attentive pooling to get the character embedding. And finally, for each sentence, they also perform the attentive pooling to get the sentence embedding based on all the character embeddings. So in this way, you will have like two embedding vector for sentence A and sentence B. And you can classify the relationship based on the to sentence embeddings. And they show that if they encode the character either by like numbered model or bit encoder, in both situations, they can perform the baselines for like the accuracy and advanced score of text classification on 2 datasets. Next, I talk about the application on text mining and classification. So here, let's say if you have a user which like he input a query in the search engine, let's say the query is about resumes with an speech, you want to infer like what is the user's interest. So we propose the attention ontology, which like organize different user interests in an ontology in a hierarchical way. So for example, we have different categories, let's say the technology, current events, and we have the different concepts, let's say the purple cell phone or cell phone for the elderly and so on. And we have different topics, the cell phone launch, the Brexit negotiation, and we have different entities as well as different events. So basically, an event means like something happened, something, some real world event. And a topic is like a topic which covers a series of events like happened in different times, but they are correlated to the same hot topic. And for the concepts, they mean like a collection of events sharing the same property. So basically what we did is like we mined different phrases from the user queries and news articles to represent the user's interest. And we discovered there is a relationship between them. So this is the framework of the what we so-called the giant system. So let's say if you have the search engine data and you have the query and you have the click documents, then in this way you have a large-scale bipartite graph. Then you can perform like a bipartite graph clustering to divide it into several subgraphs. Well, each subgraph contains several queries and documents which like they are correlated. And then based on each cluster, you can potentially extract a phrase, which may be like a concept or an event and so on. So it represents a node in the ontology. Then you can like identify there is a relationship to append it into the existing ontology graph. And based on such an organized user attentions, you can perform different applications. For example, you can tag the user interest for different users, and you can like generate stories based on the relationship of different events. You can tag documents based on the document content, or you can like perform query conceptualization based on the entities contained in the query, and there is a relationship between entities and concepts. So the key problem is like, let's say you have several short queries and news articles. Let's say you have the news articles titles. How you can like extract a phrase from this cluster of short text. So basically what we did is like we transform it into a query title interaction graph where like each node represents a unique word exists in one of the query or title. And we have different edges representing whether two words are adjacent to each other or whether they have like dependency relationship between them. Then we also have the virtual start of sentence, end of sentence node for different short text. So in this way, we have such a graph representation. And what we did is like, if you want to extract a short phrase, basically what we want to do is like perform node classification to extract the words belonging to the output phrase and perform transfers to extract the order of the different nodes. So this is what we did. So first, we perform node classification to extract the nodes which we will keep. And then we solve a problem which we call the asynchronized asymmetric travel salesman problem to find the shortest path between the start of sentence node and the end of sentence node. And each will connect all the positive nodes with the shortest path. So then along this path, we can get the order of the words. So this system is applied to different feed news recommendation functionality in different apps. And for example, let's say you have a document which is like, see this path with less than 12 per 100 kilometer fuel consumption, and then the target, the tag concept is like low fuel consumption cars. So basically, the concept like this phrase is not shown in the title or in the content, but we can know that we can use such a tag to highly summarize the semantic of the document. And similarly, this article is about the healthy receipt, and this article is about the house price trends. So you can see that the different tags can help to summarize the document's topic and the content in a very way which like matches with users' language habit. And for text classification, so in this work, they perform transductive text classification with text GCN. So basically, what the graphic exactly is like, the nodes are words and documents, and the edges are co-occurrence, which is like what the two words co-occurred in the same document, and the TF-IDF, like what's the TF-IDF between a word and document. And they model the graph with a graph convolutional network. So you can see that this is the adjacent matrix of the graph. So if both the two nodes are words, they calculate the PMI. And if I is the document and J is the word, they calculate the TF-IDF. And if they're similar, the weight is 1, otherwise it's 0. So in this way, the document classification becomes the node classification in such a graph. And in this work, like they consider to perform inductive text classification with text ing. So here the nodes are words in a document, and edges are the co-occurrence of word pair. And they model the graph with a gated graph in the network. So each document is an inductive graph, and text level word interactions can be event in it. And in this work, like it can generalize to new words that absent in training. So it's applicable for inductive circumstance. So in this way, like each document is like obsolete graph instead of like we construct a big graph for all the documents in a corpus. So in this work, like they compared the text ing compared to the previous work, the text GCN, so you can see that the performance is better in different data sets. And they also test the performance and gain with different % of training data. So basically it shows that the text ing, like the advantage is more obvious when the data set is limited. So you can see if you use just a little bit training data to learn the two different models, the text ing can have significantly better performance than text GCN. And short text classification, like they are related to different tasks. For example, the query intent classification and news classification. So you have like different short text, for example, the trees, the reviews, news articles. So the titles are short text and queries. So for short text classification, we have like several key challenges. The first is like how to deal with semantically sparse and ambiguous. Because the text is short, you have not enough content to describe the semantic information, and how to utilize limited labeled training data. Because let's say you have a large number of unlabeled short text, and only a sub amount of them have label, and how to discover different importance of different information. So let's say if you augment the short text with different information, how you can balance the importance of different information to get a better representation of the short text. So in this work, the HGT, so they performed what's called the heterogeneous graph attention network for semi-supervised short text classification. So the nodes are like the, let's say they have the different text, for example, the short topics, the short text, and they have the different topics learned from a collection of text to unlabeled text. So basically these different topics are learned by the LDA, and they also have like different entity nodes. So, and they have the different edges. So whether the text contains the entity and whether the text belongs to a topic and whether two entities are similar in terms of their word vector similarity. And basically this is a general framework. So this is a specific type of heterogeneous graph they applied. You can also incorporate other different graph elements into it. So in this specific example, we have different edges like the text topic edge and the text entity edge and the entity similarity edge. So this representation is called the heterogeneous information network, and they further propose the heterogeneous graph attention network. to learn the representation of different nodes in it. So let's say basically the key design in this network is like the dual level attention. So basically the first level is the so-called the type attention. So because you have different type of neighbors, so for each type you can have different importance. And the second level is like the node level attention. So let's say for the same type for other entities, you also have different attention ways to aggregate the information from specific entity. So in this way, we have the dual level attention, and then it can perform self-supervised training based on this structure. And in the experiments, they show that the HJT performs better than a lot of baseline measures. And also in the it tests the variance. So basically, the variance shows that both the graph structure design and the dual level attention mechanism is important for the performance of the HJT. So to summarize, we can see that the graph neural network enables us to encode multi-scale information as well as encode heterogeneous information. So based on what are your applications, what are your data, you can design like suitable or heterogeneous representation of the text and encode them to learn appropriate text semantic representations. Next, we will go to the demo part. Thank you.
Thank you, Bang. Okay, let me share my screen. Okay. So from here, we will go to our hands-on demonstration part. So we will introduce our graph or NLP library, as we mentioned before. So this is our first library to promoting the easy use of the graph and units for the various NLP tasks. So here I briefly introduce a little bit of history and future for our graph and NLP effort here. So in the last year, June 2021, really we released our first graph and NLP task. We call it V0.4.1 because that so before that we already tried some internal use of that. So from the 0.4.1, we are first publicly release this library and try to make it benefit for the whole community. So in the September 2021, we felt that so this is really a lot of the growing interest here for the whole community for this deep learning graph and NLP. So we launched our website, try to collect all different kind of resources, learning resources in one website. So in this website, we include our first survey on this domain, graph and units for natural language processing. We have included this library, we include the various tutorial, we are presenting in each of the top ranked AI conference, and we also have a workshop and many more. So in same time, we also release our V.5.1 graph and NLP library. There we are supporting a lot of new stuff there. For example, like testing with the user own data and face many reported back. And so the community is really like the library. They give us a lot of the feedback. In a very short time, we have over 1,000 stars in our library, and we see a lot of issue, and really appreciate all the community's feedback. So later we also release our V.5.5 this early year to support, for example, the model predict much easier. And also we separate the graph topology, graph embedding stuff, so that it's much easy to do the to use a library. So moving forward, so we are also going to release the graph and NLP 0.6. There we'll have a brand new configuration system so that you can much easier to use the library. And also we also support the relational GN later. Also, I want to introduce our DLG4NLP iClear 2022 workshop that it will be held in joint with iClear 2022 in April. And moving forward, so we will have more tutorial, more workshop, and also we are preparing a new book, a new graph and NLP book. Later will be published by Cambridge Press. Okay, so this is overall architecture for our GraphNLP library. So as you can see that here, we currently definitely building on top of the CPU and the GPU, and the backend library we use a PyTorch, not yet supported for the TensorFlow, but since PyTorch is very well used, so that's why we target it first. And for the runtime library, we are building on top of the deep graph learning library and Hugging Face. So the GraphNLP part is really what we are building for this library. We have 4 different layers. And the first layer is a fundamental data part for graph data and the data set. And then in the second layer, we have 5 different modules, kind of like low-level API, the graph construction module, GM module, prediction module, loss module, and the evaluation module. On top of that, we also integrate 2 popular model, graph sequence and graph tree, so that it can much easier to using these 2 high-level model to do your task. And on top of that, we support 12, I think it's 12 different NLP tasks so far, but you can definitely customize your own application using the lower level API that we provide here. So this kind of a key feature for this library, very easy use, flexible, rich set of the learning resources in our DLG4NLP website. It's high runtime efficiency and extensibility, and also have provided comprehensive code examples. So this is the next release that we are going to do here. So this is general data flow for our GraphNLP library. You have a raw data, you go through our graph construction module to get graph construction data that define our library, and then we send that to our graph embedding module to get embedding for each of the graph node, and then we will send that to the prediction module, and then depends on you're doing the classification task or generation task, so you choose your own you choose the corresponding evaluation and loss functions. So this is the computing flow for our GraphNLP. There are 2 possible scenarios. The first scenario is that you have a text sequence. You can construct a static graph construction. The low-level API is already provided there. So you can use it like a graph data topology construction, and then you can define the data embedding to initialize the embedding. And then you can optionally choose a dynamic graph construction. And if you don't choose the static graph construction, of course you need to choose a dynamic graph construction. Otherwise, that is optional. Okay, and then we send that to the graph embedding module to generate the graph node representation for each of the graph node. And then it depends on your task. It's graph level classification, or node level classification, or link prediction, or you can do the sequence or tree and graph decoder. Alternatively, that if you have input already in graph format, then you can directly just call a graph data topology construction module and then go through the following workflow. This is just showing, we have test our library with the variance of the task, use the variance of the graph neural models, and also use a different evaluation metric, try to replicate the reported result in each of the step of the paper. And this is result showing that we are able to do that. Okay, so this is like a more high-level picture to dive into the GraphNLP library. We have modules have 4 different modules and have a corresponding graph construction stuff, embedding stuff, and the prediction stuff, and loss evaluation unit. Okay, on the left-hand side, you have so many applications that we support here. You can also customize for yourself, and also have a high-level module here. Okay, so now I will give my flow to Yu to further introduce the low-level code examples for the demos.
Yeah, thanks, Minfei. Yeah, let me share my screen. Yes, so next I will first introduce some important module level APIs of the GraphNLP library. Then I will introduce like two demo applications by calling those module level APIs. So which can enable like easy which can enable us to easily like build GM-based NLP applications. So let's first talk about the graph construction module. So as we mentioned earlier, graph construction is really important. So in the current version of our library, so we provide APIs to both static graph construction and a dynamic graph conjunction. So for static graph conjunction, we provide 3 building static graph conjunction APIs, which include dependency graph conjunction, constituency graph conjunction, and IE graph conjunction. And as for dynamic graph conjunction, so there are 2 APIs. One is for node embedding based dynamic graph conjunction, and the other is for node embedding based refined graph conjunction. So for the first one, it's actually utilizes the node embedding based graph similarity metric learning function we previously introduced. And for the second one, it's actually tries to combine the benefits of both static graph and dynamic graphs. So here are some examples how we can call dynamic graph conjunction module APIs. So for the first one, we can see that here are some important parameters here. For example, the symmetric type parameter. So here we can specify which kind of graph similarity metric learning function we want to use. So like either it's attention based, cosine based, and so on. And there are some other important parameters like a top K neighbor, epsilon neighbor. So these are parameters we can enforce the sparsity of the learner graph structure. And also there are some regularization parameters like the smoothness ratio, connectivity ratio, and the sparsity ratio. So these parameters can be used to control the quality of the learner graph structure. And for the node embedding based refined graph conjunction API, so one additional parameter we introduced here is this init adjacency alpha. So this is actually a hybrid parameter which can be tuned to keep a trade-off between the intrinsic static graph and the implicitly learned dynamic graph. So next, let's talk about the graph embedding initialization module. So actually, how to initialize the node embeddings plays a very important role to the overall performance of the GN-based model. So in our library, we support different strategies to initialize the node embeddings. We support both the single token node or edge or multi-token node edge. So here we are talking about whether the node or the edge contains a single token or multiple tokens. And we also provide various building strategies for node or edge embedding initialization. So here's a non-exclusive list here. So here, let's talk about the multi-token node scenario. So we have a graph of nodes. Each node contains, for example, a text sequence, which means like it has multiple tokens. So how can we initialize the node embeddings? So here we provide multiple strategies. For example, the W2V means water to vector. So we can use pre-trained water to vector like the graph embedding to initialize the token embedding, and then we can compute the average embedding to initialize the node. And here the W2V by STM means that we, instead of doing average, we can apply a by STM model to the test sequence of the node to initialize its embedding. And here we can also try to leverage the bird embedding. For example, in this W2V bird by STM, so we use both the glove embedding and the bird embedding to initialize the each token in the node. Then we apply a by STM to learn the overall vector representation of that node. So in short, we provide many useful building strategies to initialize the node embeddings, and those strategies have been proven to be effective in the existing literature of DLG4NLP. Yes, next I'll talk about graph embedding learning module. This is also a very important module. So here we provide some common GN variants like GCN, GAT, graph stage, and GGN. So for each type of GN we provide, we have an important parameter here, which is direction option. So remember that previously we introduced the bidirectional GN. So here for each type of GN, we allow users to specify like whether we want to use a unidirectional GN or bidirectional GN. Like for bidirectional GN, whether we want to use the bifuse version or the bistep version. So we can easily specify it when we call the GN API. And another important parameter is this use edge weight. So this is it's extremely helpful if we want to use dynamic graph conjunction, because dynamic graph conjunction is able to learn a weighted graph, and the edge weight is really important. And we want to use the edge weight information during the message parsing. So you can achieve that purpose by like turning on this use edge weight. Yeah, next I'll talk about prediction module. So basically we categorize NLP tasks into two categories. One is the classification task. So for classification tasks, we provide APIs for node level classification, graph level classification, link prediction, and so on. And we provide some commonly used pooling mechanisms, graph pooling mechanisms like the average pool, the max pool. And for the generation task, we provide building APIs for sequence decoder, like the ARM-based decoder, and also we provide API for tree decoder, and for each type of for both like a sequence decoder and the tree decoders, so users can easily employ the attention copy coverage mechanisms by specifying the corresponding parameters. And by the way, we also provide a building high-level graph to sequence, graph to tree APIs. So this is basically like config in, model out. So these model level APIs could be easily used for many graph to sequence or graph to tree problems. Now let's talk about the dataset APIs. So because different types of NLP applications requires different formats of the input and output data, so we categorize those variants like use cases into the following types of scenarios. One is like text that include like text to text, text to tree, text to label, sequence labeling, double text to text. And based on the building dataset, low-level dataset APIs, so users can easily build their own dataset API by inheriting the low-level APIs. Like here, we build the check dataset API based on the text to label dataset, because we want to use that dataset for the text classification task. Yeah, let's talk about the inference wrapper. So we also provide APIs to enable online deployment. So this is basically raw data in and final predictions out. So we provide inference wrappers for both the classification task and the generation task. Yeah, so that's the introduction for the module level APIs. So next, I would talk about like two real world demos, which we can easily build based on the previously mentioned module level APIs. So first, let's go to our Graph NLP demo GitHub repository. So we have a GitHub repository hosting the demos built upon the Graph NLP library. So in order to run the demos, you will need to follow the environment setup instructions to install the Graph NLP library. So you also need to install some other toolkits like the Stanford NLP toolkit, because in our library we use it. We use this for static graph construction. So remember that like we usually do static graph construction during the pre-processing stage. So this can help us build like a dependency passing tree, IE graph, and so on. And then you can just open the Jupyter notebook and you can directly run these demos. So the first demo we'll be introducing here is the text classification task. So this is a very, like a simple task. So we are given a piece of text. We want to predict a label for that piece of text. So that's falls into our text to label scenario. So in this tutorial demo, so we will use the GCNLP library to build a GCN-based text classification model. So this model consists of a graph construction module, the graph embedding module, and the prediction module. So we will use the previously mentioned module APIs to build this GCN model and evaluate it on a data set. So you can directly run this demo here if you already installed, follow the instructions to install the library and other packages. So let's go back to the slides to talk about some important pieces of that demo. So here's the model architecture. So as we can see, like here are some important components here. So for example, we will need to call the graph embedding initialization API to initialize the node embeddings. And we will optionally, we can choose to use like a static graph construction or dynamic graph construction. So for dynamic graph construction, because it does graph construction, graph structure learning and graph representation learning on the fly. So we will call this dynamic graph construction function when we running the model. So that's why this appears in this PyTorch forward method. And then we can call the GCN API to learn the graph embeddings. And then we have here we have a graph classifier for the prediction module. Yeah, so as for the graph embedding initialization, so we have previously introduced this like a module level API. So here we can define whether it's a single token scenario or multi-token scenario. You can specify various embedding strategies to initialize the node embeddings. For example, we can use this W2V bias team strategy. And yeah, and this like graph embedding initialization API can also be easily customized. And so this is for the dynamic graph construction. So as we previously mentioned, there are some important parameters here. And this can also be easily customized by inheriting the our provided low-level APIs. So this is for how we can call a graph stage API. So there are some important parameters here. One is this direction option. So we can choose to use like bi-step, bi-fuse versions of the graph stage model. And this is the prediction module. And this is the dataset API. So so here some important parameters like include this graph name, because if we want to use static graph construction, which is conducted during the preprocessing stage, so we will need to specify it when we create in this dataset API, like whether it's dependency graph or IE graph and so on. Yeah, that's next. Let's see another our second demo about semantic parsing. So semantic parsing aims to like generate a logical form of the input natural language sentence. So this can be quite helpful for many applications like a question answering, because we can execute the generated logical form against some knowledge base to fetch the answers. So let's go back to the demo page. So here we have a demo for semantic parsing. So here the model consists of three important components, which are like graph construction component, the graph embedding component, and the prediction component. So in this demo, we regarded this semantic parsing task as the graph sequence task. So we can directly use the built-in graph to sequence model API to easily build the model. Let's go back to the slide. So as we can see, we just need one line of code to create this to build this graph to sequence model by calling our model level API. Yeah, that's the demo part. Let me pass it to Lingfei.
Okay, thank you, Yu. So now let's finish our last part. It's future direction and conclusion. So it's already take quite a long time than we expected since we have a lot of discussion here. So I really appreciate, everyone who stay for such a long time and still with us. Okay, so I will briefly just go through the future directions and then we'll conclude this tutorial. So regarding the future direction, so we can see that the graph neural nets and NLP are two hot topics that have been, showing here in the IQLab 2020 submission. There are a lot of things going on here. There are great potential, but combine them is even more interesting. That's because that you have so many things you can do together. So the first thing that you can consider that so how shall we do a good graph construction for NLP? Because that's very important for graph neural itself. If graph itself is not good enough, then you won't able to get any good result with graph neural nets. So we have been talking about the dynamic graph construction, right? But if you look at the literature, there's very, very few papers using dynamic graph construction. Okay, so I think this is really large and explored. So there's many opportunity to doing either research or from industry perspectives that you can use this approach to do a graph construction. Of course, typically if we are able to combine the state graph and dynamic graph, this should be performed better than a single modality. But how to construct such a good dynamic graph? This is not not very long. Okay, and also how to make the dynamic graph construction itself scalable is also a very important problem if your graph node is large. The second part is how to scaling our graph nodes for the larger graph. Luckily, we already have some solution on that. This is one of the most active subdomain for the graph nodes community. However, still we want to see quickly, right? So for example, multi-relational or heterogeneous graph nodes, how can we scalable to the logic graph, for example, larger than 1 million size? Okay. For GN transformer, I think you have heard a lot about GN transformer, right? And you heard a lot about the pre-training. All these things that means that two learning paradigm are all very important to the NLP community. So how can we effectively combine the advantage of the both worlds? Is also an important thing to consider. The last one is the graph learning that Professor G have talked about a lot of things regarding the information instruction using the graph model. However, can we develop a more generic model for solving the graph transformation problem in NLP? So this is a very interesting direction. And also how to generally to take into account the text and catchy reasoning for NLP, and also how to incorporate the source and the context into the logic graph conjunction so that we can do the conjunction and the verification. So, okay, so with all this summary being summarized, so let's then conclude this tutorial. So first of all, deep learning graph NLP is a really fast growing area today. Okay, so the thing that graph is really very it's magic thing that people love is because it really can naturally encode the complex information so that they're able to bridge a gap, so to incorporate both domain knowledge and also power deep learning. But for any kind of NLP task, you have to consider two problems. First one is how can we convert the text sequence into a basic graph? We have mentioned the directed graph, multi-linear graph, picture graph, but you have to do yourself, right? Of course, with our library, you are able to do that very easily. The second part is that how to determine the appropriate graph representation learning technique. This is really depends on what kind of graph you have at hand. So finally, we are going to show all these links, right? So to help community to make easy use of graph news for NLP, the website contains all the learning resources. I have survey, library, demo, and also I use it in GitHub literature list that we have been reviewed. Okay, I think that's all for today's tutorial. So I see some question here. Let's see. We already, okay, that's use comments. Okay, any question? Yeah, if you have any question, please unmute yourself. So otherwise, I will, yes.
It's outstanding tutorial. Thank you so much. Really appreciate
Thank you so much, yeah, for staying with us for such a long tutorial, yeah. But hopefully, yeah, we can provide some really useful resources and perspective on how to leverage the deep learning graph technique for NLP problem.
Yeah, very, very well done. And just, you know, probably should have a lot more time.
Yeah, but please drop us an email, anytime. Yeah, if you have any question. And we already posted the website, the DLG4NLP website, and we will post the slides and also the recorded video very quickly. Yeah. So, you can come back and check out learning material. And you are also welcome to forward that to your colleague, if your colleague is interested in this topic. Okay. Okay, I think that's all for today. Thank you so much, everyone. Have a great day. Bye-bye.
Thanks, everyone. Bye.
Thank you.